2026, a 6-day faculty development program on Smart Machines 4.0, Intelligent Monitoring and Digital Twin for Data-Driven Engineering Systems. Ladies and gentlemen, 3 days we had wonderful sessions by various experts from various industries across the state. Definitely, I hope the last 3 days went on well and you had fruitful information. And this day will be another quite interesting day. The 3 guests who are going to share their knowledge and expertise on various topics. So let us hope and lend our ears to the words of their resource person. So on behalf of Department of Mechanical Engineering, Knowledge Institute of Technology, Salem, Tamil Nadu, I do take this opportunity to welcome the resource person of today's first session, Dr. Kanchan Agarwal, who is a Senior Technical Leader at ZF Group, Chennai. So she is the resource person who is going to address on the topic condition monitoring techniques. At the same time, I do welcome all the participants from various institutions across the state for this 6-day FDP program, especially this 4th day. So with this, welcome note, I take this opportunity to introduce our resource person briefly. She is a distinguished professional with expertise in data analytics, machine learning, statistical modeling, and intelligent automation systems. She earned her PhD in seismic data analysis from the Indian Institute of Technology, Madras, that is IIT Madras, and has been actively contributing to the development of advanced data-driven solutions for industrial applications. At ZF Group, she leverages cutting-edge analytics and machine learning techniques to enhance operational efficiency, develop scalable intelligent systems, and support digital transformation initiatives. With a strong academic foundation and extensive industry experience, she brings valuable insights into the emerging trends and applications of intelligent monitoring technologies in modern engineering systems. Today, she will be delivering a session on condition monitoring techniques, where she will share her expertise in advanced monitoring approaches, data analytics, and predictive strategies for improving the reliability and performance of engineering assets. So with this, a brief introduction. Again, I do welcome the resource person and also the participants for this morning session of 4th day. Thank you, and over to you, ma'am.
Thank you. Thank you so much for the warm welcome. And thank you everyone for joining today's session. I'll just quickly share my screen. Yeah. Let me know if it is up.
Yes, ma'am. Make it full screen, ma'am. Will it be?
I have already made it full screen.
Okay, fine.
Visible. 1 second. I'll just reshare because I think because of. Yeah, I hope now you can see the full screen.
Yes. Now it's okay.
Okay. So, warm welcome everyone. Good morning. Thank you for being here. Introduced, I am Kanchan Agarwal and I am a senior technical leader at ZF Commercial Vehicles. Today we are going to spend next 1.5 hours on understanding how the physics, signal processing, and machine learning can intersect at the same time, and can sit together and come up with a very beautiful solutions or approaches which can help you to solve the day-to-day problems, especially when it comes to machineries, vehicles, or any equipment. So the topic which I'll be discussing is condition monitoring techniques. By default, this terminology itself sounds very maintenance term, but as we will walk through, we will see that more than maintenance, it is a very good combination of the physics as well as the data-driven approaches, and how these two things come together to solve the fault detection issue or the equipment failure issue at hand. So agenda for today's talk is as follows. I'll first briefly discuss my journey till here, starting from the BTech days, and then we will discuss what is condition monitoring, why does it matter to work or to learn about condition monitoring, and how can it help us to solve some billion-dollar failure story. I'll give a use case study of Toyota, where we will see that Toyota had to spend huge amount of money and as a penalty because of some failures which has happened, and those could have been easily avoided if condition monitoring techniques were utilized in order to detect those failures beforehand itself. And as we will see in upcoming slides, there are a lot of techniques when it comes to condition monitoring, but I'll be focusing mainly on two techniques, which is vibration analysis and data-driven analysis in details, and discussing the other in short. So we will end up today's talk with some decision metrics, where I'll show for what type of equipments or components, what type of condition monitoring technique is more suitable and why you should adopt that. And after with this, I'll conclude the talk today. So coming up to my journey till here, so I started my journey in 2010 as the BTech candidate, where I am by heart electronics and instrumentation engineer. After finishing my BTech, I had spent nearly five and a half years in IIT Madras, where I had pursued or learned about how to do research, and I have pursued both master's and PhD degree there in this five and a half tenure. And during my PhD work, I have looked at the earthquake detection, which on surface it sounds completely unrelated to condition monitoring of industrial machines, and it is somewhat unrelated if you just look at the physics behind each domain, which is earthquake and the industrial machines. If you just look at the domain perspective, both are entirely different domains. However, when you look at the data perspective of it, so there is a very interesting catch there. Whatever I have done or learned during my PhD days from data perspective, which is techniques or statistical approaches or time frequency driven approaches to detect the onset of P wave, with the core idea during PhD and in condition monitoring are kind of similar. In both the domains, what we are actually looking at somehow figuring out a small change in the signal. For earthquake detection, my objective was to figure out a very small amplitude, short-lived signal buried in the noise. And in condition monitoring also, what we are looking at whenever the characteristics of a parameter or some sensor data or some component or equipment starts to change. So our objective here is to just detect the when it starts to deviate or change from its normal behavior. So even though the domains are entirely different and unrelated, the data connects both the domains very beautifully. So that's why I said in the beginning that in this talk, I'll be trying to establish the connection between the physics, using the physics and the data analytics. And data analytics kind of becomes the universal language nowadays, which tries to, or which brings any domain under the one umbrella, and you can connect dots or use same technique in any domain, irrespective of whether you are new to that domain or you have good experience in that. Without spending more time here, I would just, as when it comes to my industrial experience, I joined Honeywell immediately after my PhD, where I had been looking at, I was looking at data-driven approaches or solutions for making the buildings more smarter. Mainly, we were looking at fault detection in HVAC systems, energy optimization, and stuff like that. Everything related to data-driven analysis. And then in 2024, I moved to ZF commercial vehicles, where again I've been looking at data-driven approaches or techniques. These are with respect to the commercial vehicles. So even if you just see in my journey, I have been working, or I have worked in 3 different domains, which are completely unrelated, but data is the common thread which connects all of them. Now moving ahead in the presentation, so I will start with what is condition monitoring. So most of you must be aware of this terminology, what is condition monitoring. Any one of you wants to take a shot on explaining, or if you are aware of what it is, just want to hear about your thought process or what you know about condition monitoring.
Ma'am, good morning, madam. We have studied technically, that is maintenance, predictive maintenance, breakdown maintenance, like that we have studied. It may be related that kind of maintenance.
Yeah, rightly said. It is related with the. It is a maintenance technique by heart, but there is a very subtle difference between condition monitoring and predictive maintenance. Though both of them are very closely related, both of them works with the data. Both of them tries to figure out a small change in one of the features or characteristics of the equipment, and based on which they declare a fault. But I'll be explaining in details just in a couple of minutes the difference between condition monitoring and the predictive maintenance. But before going there, so if you look at the formal definition of condition monitoring, as you can see on your screen, it is basically identifying or detecting the occurrence of the fault before it actually happens. So what we are trying to do here is, or what the objective here is, to figure out when the component or machine or equipment or vehicle starts to degrade. So before the degradation actually happens, you try to figure it out or detect or estimate that early, and then take the necessary actions so that you can prevent. There are like a lot of benefits which I'll discuss shortly, but the main objective here is to detect the occurrence of the faults or anomalies in your equipments bit early than as compared to the actual damage. So it's basically a maintenance strategy only. There is no denying in that. But if you look at the maintenance strategy, the maintenance has been evolving from being reactive to being prescriptive. So nowadays, all of you must be aware of this ChatGPT and Claude and all these LLM based or agentic AI based solutions which are already there in the market. So, and all of us are using them. So if you look at the transition or the movement from the reactive to the prescriptive, then it's really commendable how things are changing in industry. So when it comes to the reactive type of maintenance, so reactive maintenance is you let the equipment break, and once it breaks, after that you fix it. That is reactive. So damage has already happened. You are just doing the damage control now. So you end up paying more money. You end up your waiting period increases in the sense that the downtime of the equipment or the vehicle increases. You can't use the equipment till it is repaired. So these are some of the drawbacks when it comes to the reactive or why we should avoid reactive maintenance. Now, as we move from reactive, then we have time scheduled maintenance. So time scheduling maintenance are something like when if you have a car, then you do take your car for servicing every 10,000 kilometers, or you change your tires after your car has driven 40,000 kilometers. So these are like some standards and fixed schedule maintenance which you usually do in order to keep your asset or your vehicle in good health. So that is time scheduling or time based maintenance. Now the issue in this or the problem with this type of maintenance is there is nothing wrong as such, but the thing is, if your tires have not worn out to the extent that you need to repair it, you will end up paying the money to repair your tires because of the timely scheduled maintenance. But instead of this, if you have a way to figure out or to understand from data or from sensor data that when your tire starts to degrade, that could be easily before, that could be even before 40,000 kilometer or after 40,000 kilometer, irrespective of the fixed threshold. When you have that type of metric or information available to you, then you can take more informative decision. Let's say some car is being driven on a very mountain roads, so obviously that roads is bit rough, so that tire will worn out bit faster as compared to a car which is being driven in the city where the roads are very smooth. So both the vehicles have traveled 40,000 kilometers, but the tire conditions for both the vehicles is very different. And you do not need to pay same amount of money for maintaining both the vehicles. Your city vehicle require less amount of expenditure because it has not worn out that much. So in fixed maintenance or scheduling, we miss out on these aspects. We end up paying a fixed amount of money at a fixed interval because we don't have intelligence or information about the asset condition or health. Now, third pillar comes about the condition monitoring. This is the main focus of today's talk. What we do here is, here we look at the census data. Then using the sensor data, we try to figure out whether whether something is has started to change or deteriorate, or it is still in good health. So we continuously or periodically monitor the asset health using sensor data, and based on that we make a decision whether it should go for maintenance or it is still good to go for another 5,000 kilometers. So you or we end up making an informative decision here instead of just giving our vehicle for maintenance on a regular interval. Now, the subtle difference which I was talking about between the condition monitoring and the predictive monitoring, the maintenance. So there is more or less both of them uses sensor data. Both of them looks into the history of the data or historical data to understand the vehicle condition or your asset condition, and then try to figure out using some ML techniques or some other data driven approaches, try to figure out if something has started to change in as compared to your normal behavior. So this is common in both, but the difference lies in your condition monitoring only talks about whether things have started to change. That's all it will do. It won't be able to tell you so for example, if I take the tire example, replacement example again. Now here, I instead of replacing my wheels of the car every 40,000 kilometers, if I chose to replace it at let's say 35,000 kilometers, because I know based on the data that I'm getting from my car that I need to replace it now. It has already started to wore out. Predictive maintenance will tell me instead of replacing at 35, you are still good to go for 2 more years, or you are still good to go for 2,000 more kilometers. And if you replace it after 2,000 kilometers, then also there is like you are still in the safe zone. So that's what predictive maintenance will do. Condition monitoring will only tell you whether the system has started to degrade or not, whereas predictive maintenance will also tell you how much remaining useful life is remaining or is left, or for how long you can use the asset without any failure. So that's a very subtle difference between these two techniques. Otherwise, more or less, both are data driven, and the underlying concept more or less is same for both. Now, the last one or the most recent things which are coming in when it comes to the maintenance of a asset or a system is the prescriptive maintenance. Now, this is where the industry is heading right now. Here, AI is not only used to predict whether there is a failure or not, or how long we have before we need to replace the entire component. It is not just restricted to that. It is also recommending exact actions and what parts and the time window. So it will tell you what needs to be done. So far till predictive maintenance, it is only, or the maintenance approach or techniques will only tell you whether you need to replace your component or not. And at max, it will tell how long you have, but it won't tell what you should do. So for tire, again, if I take the wheel example, it is highly possible that I do not need to replace my entire tire or entire wheel. I just might need to just do a small fix in it, and then it is still good to go for 5 more years or 5,000 more kilometers. So that type of prescriptions or prescriptive analysis is now possible due to LLMs or this agents or digital twins. These type of stuffs are now allowing the industries or the users to get the prescriptions as well apart from the predictions. Any questions? Feel free to stop me anywhere if you have any doubts. So moving on, we have just now learned what is condition monitoring, or what a different type of techniques or strategies are available in industry for maintenance. We have just learned that part now. Moving on, why condition monitoring is important, or why we should worry about it. So if you look at it, either it's condition monitoring or predictive maintenance, both of them mainly focus on early fault detection. So you detect the fault before it actually happens, and that saves you money. That not just it saves you money, but it also reduce your downtime. So your unplanned downtime will be reduced, because we are able to identify the failures before it actually occurs. Therefore, we do not have to send it for repairment. That reduces the downtime or the unutilization period of the asset or vehicle. Now, second thing is safety is increased. This point is actually quite interesting if you look at it, how safety is related to condition monitoring. But because condition monitoring allows you to or ignore or fix the issues before it actually occurs. So some issues can be very critical, especially in machine driven or heavy machinery industries, where we have heavy machines, and accidents can happen anytime. So their condition monitoring can help to increase the safety protocols within the organization or the industry, because we are able to identify the failure before it actually happens, or the damage actually happens. The necessary actions can be taken, and hence the failure, or the machine failure, can be easily ignored or prevented. Basically, not ignored, it can be prevented by taking the right actions at the right time, and this will reduce the risk for personnel, and it will improve the safety protocols. Uh, Following the similar lines, it also allows you to optimize the asset performance, because we are able to monitor the equipment or asset continuously. We will be able, it will allow us to utilize the resources or the equipment in a more optimized fashion. Without impacting the performance of the equipment. So thereby the overall performance of the asset or the vehicle can be improved if you have a condition monitoring based approach applicable in it. Because your asset performance is increasing, by default, your operational efficiencies will also increase. So these two are kind of interrelated. If you increase one, the other will increase, especially if the performance is increased, your efficiency will increase. Maintenance cost will be low. We have already covered this. And then extended lifespan. So this extended lifespan is also revolving around the same point, that since we are able to identify the wear and tear early before it actually happens, so with the right actions, we will be able to protect the equipment or vehicle and to avoid the damage. So this will lead to extended lifespan, which in turn will result in the higher ROI. Any questions? Okay. So now I'll just talk about a case study, which is very interesting, and this actually helps us to understand why condition monitoring is so important, and how much the dollar impact. Basically, in industry, everything is about money. Whatever project or problem statement we work with, it has to, at the end of the day, it has to make a good amount of money. The company has to earn from it. So Toyota ended up somewhere around 2009 and 2011. Between this period, these 2 years, there were three very critical issues with the Toyota cars, and there were huge number of recalls that happened. Toyota recalled almost 9.1 million vehicles because of these three issues. So before going to the details of the case study, I'll just talk a little bit about the three failures or the issues what users were facing in the Toyota car. So the first one was the floor mat entrapment. So what was happening was the floor mat in the car, or the car mat at the driver's side, it was so thick that sometimes the pedal was getting stuck in it. So if a driver presses it with a huge amount of force, or that usually happens when we drive, so it was getting stuck in the floor mat or the door mat. So because of that, it will get stuck. Because of this, there was a delay in returning it to the normal position, and also there was this. How do I put it? So this was basically a mechanical issue. It was like there was nothing wrong with the system as such, but it was because of the thickness of the mat which was being used in the Toyota cars. The pedal was getting stuck, and which was resulting in uh, uh, a huge accident also happened because of this, and this was resulting in some issues, and a lot of users have complained about this. Now the second issue was about the sticking accelerator pedal. What happens in the pedal assembly is, over time when the conditions are very humid, so due to natural wear and tear, the pedal there will be increased friction in the pedal assembly. Because of this increased friction, the pedal, once it's pressed, it will take some extra time to return to its normal state when it is not being pressed, to its idle state. So that time that it will take, it was almost doubled in Toyota during these 2 years. And it was ideal behavior is it should return back to the normal or ideal state within zero point 0.3 seconds. But during that period, because of the stickiness of the accelerator pedal, it was taking around 0.8 seconds to return back to the normal condition. So this was the second issue or second problem which users were facing. The third one was more on the software side. So Toyota had vehicles has something called ABS, anti-skid braking system. So it's a braking system. What was happening was the due to the during regenerative braking, the transition of the brake, the software was incorporating or including some short delay. The delay was very, very small. It was hardly 0.2 seconds or 0.3 seconds, but there was some delay in because of the software in the response time. So because of the delay, when the brake was pressed, what was happening was the vehicle will stop after an increased distance. So ideally, if it was supposed to stop within like 5 meters, now because of the delay in the braking signal, it will now stop at maybe 10 meters. So that delay was observed, and this looks very simple, but it is very crucial when you are driving in a very heavy traffic scenarios where you have a vehicle ahead of you and you are pressing the brake, and you might just hit the vehicle in front of you. So these were the three main issues which were being faced by the customers during those 2 years. Now coming to the case study. So what happened was the users were facing these three issues only, and the first complaint which was received was in 2004. So there was this complaint was about the flat floor mat entrapment only, but the first complaint that Toyota has received was in 2004. Nothing happened. No one took any action because it was not considered a very major fault at that time, because the number of complaints was very less. So no actions were taken during 2004. Then in 2007, in these 3 years, the number of complaints increased, which has resulted in few recalls of the floor mats. Till 2007, Toyota has only recalled the mats, not the entire vehicle. So, and the number was also very small. It was not a huge number, so it was still acceptable. But then the changing point came in 2009. In August 2009, there was a car crash which happened, and in US it happened. And there, when the highway authority looked into the car crash, so what they figured out is the car crash happened. In the first report, they mentioned it was because of the floor mat entrapment. But when they looked or dived deeper into the actual reason, they figured out that it was also because of the stickiness in the accelerator pedal. So this resulted in opening the case further, and it became a very huge case because the person or the family which was involved in this car crash was the police officer family, and therefore it became a very huge case. And if you just Google it, you will find out tons of documents on this. Post this, the National Highway Association in US, they have looked at the previous complaints or the cases, not of the accidents, but of the complaints. And because of this, the complaints which were raised before, those things were also opened. Then in 2009, November was the first time where Toyota had to recall a majority of the vehicles. It had to recall 3.8 million vehicles in 2009. And the reason was one of these three only. And the main trigger point for this was this accident which happened in 2009. In Jan 2010, the sticky pedal recall happened at a much faster pace. So apart from this 3.8, it had to recall 5.2 million vehicles again. So just think of from the company perspective, how much money it has wasted, or it had to invest in order to fix all these issues. Recalling involves cost, fixing involves cost, and then giving them, and it even paid some compensations to the people for the time period they were not able to use the vehicles. It had to pay some compensations as well. Then final settlement happened in 2014, and Toyota ended up paying $1.6 billion as just as the settlement money or price. So all of this could have been avoided if condition monitoring techniques would have been used. So when the first complaint came, that time if we were monitoring the parameters, the pedal assembly parameters, then we could have very easily figured out that something is changing there, and the actual fault, it might have taken some more time. Maybe 2005, by 2005 they would have identified it, but it would have stopped Toyota spending so much money because of these failures. All of them are easily identifiable or detectable by condition monitoring techniques. So floor mat extrusion can be easily, the way condition monitoring can tackle it is by looking at the pedal position sensor data as well as the vehicle speed data. So if you look at the cross correlation of these two data sets, then you will be able to figure out that the pedal is stuck and the pedal is getting stuck. So that thing will be very obvious because your vehicle is not you even though you have left, there is no pressure on the pedal, but the vehicle is still moving because it is stuck, and it is the acceleration is very high during that period, even though driver is driver is not pressing the pedal. So pedal position will be fixed during this scenario. So that could have been easily identifiable just by pure data analysis or condition monitoring techniques. Likewise, for the second issue or fault which was there, which is accelerator pedal stickiness, this is also mechanical issue, and this also could have been easily identified by condition monitoring. Just by placing a load cell on the pedal assembly. So this load cell will monitor the friction force, and it will notify, or we will be able to have either some threshold, or I'll discuss the techniques in details in upcoming slides. But just layman terms, we could easily have a threshold where we can say if the friction increases beyond a certain threshold, then that means something weird is happening, and we need to inspect it more carefully. So that degradation could have been easily identified with condition monitoring techniques. And for anti-braking, even though it was a software issue, still condition monitoring could have tackled it. However, the scope of condition monitoring in these mechanical issues is much higher. Having said that, for braking software issue as well, just by monitoring the braking performance and regenerative to friction brake transition, we will be able to identify the fault detection early. So we will be able to figure out that there is some issue or some delay in the response time. And once that has been identified, the responsible person could have looked into the software drift in the brake. braking response. So all three of them could have been easily identified in 2004 itself, which would have saved Toyota paying such a huge, hefty amount as settlement. And it had to recall 9.1 million of vehicles. And this is an approximate number. There were 37 death attributes attributed because of one of these reasons. And this particular case became the trigger point for this. And not only the settlement payment, the sales number also. So all these things, what has happened in these 2 years, had a huge impact on the Toyota vehicles sales post January 2010. So there was a reduction, 16% reduction in the sales of Toyota vehicles in US post January 2010. So I hope this has motivated why we should look into condition monitoring. Without wasting any more time, now I'll just go deeper into the different stages of condition monitoring. So as you can see from the slide and whatever I have been discussing, it's condition monitoring involves data analysis. Data analysis is kind of if the physics behind the vehicle or the asset or component is the heart, then uh, think of data analysis as the blood that makes sure the heart will stop pumping if there is no blood, or the other way around. So both are needed, and you can't go through without any one of them. So likewise, condition monitoring, we need physics behind to understand the system perspective, and then we need data to make the system talk to you without interfering with the performance of the system. So every condition monitoring system, regardless of the technique, regardless of which approach you are taking, it follows the same pipeline. It will always have 6 stages. The first one is the setup. So the first step is identifying which components are crucial in your asset or vehicle, and then setting up the right sensors at the right locations. So sensor location also plays a huge role, which I'm not covering in today's talk. Today I'll be focusing only on the condition monitoring techniques. But sensor placement, setting up the sensor, identifying what sensors are needed, where it should be installed, and what parameter it should monitor or it should sense. All these things becomes the first stepping stone when it comes to condition monitoring techniques. Once we have the sensor, the second thing is the data acquisition. Why data acquisition is important? Because each sensor will sense data at a fixed interval. What I mean by fixed interval is, let's say you have vehicle speed and you are getting vehicle speed at every 5 milliseconds. Now you have engine RPM. Engine RPM, let's say you are getting every 30 millisecond or every second, every 1 second. So the interval or the frequency at which we are getting data becomes very crucial in identifying what type of fault we are trying to identify. Therefore, data acquisition needs to be very proper. We need to have a very, systematic provision to sample the data at the right frequency, then to collect and store it somewhere so that it's available. So all these things becomes very crucial. Therefore, data acquisition is also a crucial stage of condition monitoring. Now, third stage is the signal processing. Once we have data, we have to know what to do with the data. But in order to figure out what to do with the data, we need to figure out how informative the data is. So not every data is informative, and not every informative data you can extract information very easily because of the presence of noise. Whenever we work with a real-time equipment system or vehicle, their noise is unavoidable. You will always end up getting some noises. Or you might need a feature that needs to be extracted from the data. So signal processing will take care of all these aspects. It will do filtering if you are interested only in a specific frequency range. And if your data is very, very noisy, then it will remove the excessive noise or extra noise. It will also look at the feature extraction and any transformation, whatever is needed, it will do. So signal processing is very much needed. And if you don't clean your data properly, so in that case, even if you have a very good approach or very good method for condition monitoring, your system is bound to fail. You will end up in getting either a huge number of huge number of false detections. So either fault is not there, but you are detecting it, or you are missing out on some crucial faults if you don't process your data or you don't clean your data. Now the next stage comes is the assessment. So this is the core technique or core strategy what enables identifying the fault. So what it does is it compares if some features has been extracted in the previous stage, then it will use those features, or it will use pure time domain properties or frequency domain properties, or some properties or basically processed sensor data, compare it with a baseline or threshold. And if it exceeds the baseline or threshold, then it means there is something wrong is happening. If it is well below thresholds or baseline, then everything looks good and you keep monitoring. So this is how we monitor things. The fifth stage comes of the prognosis stage. So here what we try to figure out is based on your condition monitoring assessment, now the respective person who is responsible for scheduling the maintenance call and all these things will schedule maintenance or will take or decide what needs to be done, and in the last stage the necessary actions will be taken. So for example, in prognosis, if based on the condition monitoring output, person might be looking at how long or how much life is left, or he might be looking at when he should schedule the next servicing or maintenance. So once it decides that the stage 5 ends there, and then stage 6 comes into picture when he takes the action for that. So where he will schedule the maintenance, or he will use the equipment or asset till the remaining useful life is there. So the monitoring system is also updated with the new baseline data, and that's how the entire all the 6 stages work together in order to detect the fault, and also to figure out here. So if you have noticed here, the remaining useful life, or this when the maintenance should be scheduled, these parts are not part of the algorithm or the technique. Someone else is doing that for you. So, but if it was predictive maintenance, this would be also part of the technique what you are using in order to find these things. So this will become the objective in predictive maintenance, whereas in condition monitoring, your objective is just to figure out whether there is a fault or not. Any questions? Okay, then I'll move ahead. So now going deeper into the techniques, what different techniques are available for the condition monitoring. So as you can see on the screen, these are the 12 major condition monitoring techniques. I have tried to cover majority of the techniques in this slide, but since there are different ways, if something is missing, then there might be one or two different ways of approaching the same problem which might have been missed, but these are the major techniques which are available in literature. So so we have vibration analysis where we look at the time domain signals, and then we also look at frequency domain. So anything which has to do with the vibration, those type of sensor data is analyzed in the vibration analysis. Infrared thermography is where imaging infrared sensors are needed for this type of techniques. So basically, if you look at each one of this, so it's very evident depending on the type of sensor involved, the technique name has changed. So for example, if you look at ultrasonic monitoring, here you will have ultrasonic sensors. You need ultrasonic sensors to get the data, and once you have the data, then you will again follow these 6 stages in order to figure out whether there is a fault or not. So it all depends on what type of sensor is being used, depending and what type of fault we are targeting. Based on that, these techniques are widely used. Out of these, if you look at performance monitoring, visual inspection, and data driven, so these are kind of cross, they cut across all other technique. So data driven and performance monitoring, these are something which are very easily applicable to any of the, irrespective of what sensor data you have. These techniques will be can be easily applied. So I can very well use any ML model for ultrasonic monitoring as well, or I can use it for radiation analysis also. Once I have cleaned my data, I can fit any ML model to that. So the last three are kind of generic, in the sense that these three are not dependent on the type of sensor involved. uh, in fact, this network and frequency response also, the last four are generic, whereas till radiation analysis, these 8 techniques depends on what type of sensor you are using. Depending on the sensor used, the technique name has been derived. So now we'll be going into detail for vibration analysis and data-driven analysis. So when it comes to vibration analysis, it is most widely used or deployed condition monitoring technique for rotating machines. So anything which rotates will definitely generate vibrations, and this technique targets only those type of systems. So any rotating machine will fall under the scope of vibration analysis. What it detects is, it will detect any misalignment, or if there is any imbalance, or if there is any wear and tear in the bearings. And here I have mentioned in detail. The reason I've mentioned these 4 things in detail, because I'll be illustrating using bearing wear data, and the fault has been introduced in outer race, inner race, ball, and the cage. All the 4 places fault has been introduced, and then we will see. That's why this has been explained a little bit in detail here. And any looseness, so if something is loose in your system, then also you will see vibrations. So a very basic or classic example is the lug nut in your wheels. If that is loose, so your wheels will start to wobble, and the way you will observe that in your data is, you will see huge oscillations in your wheel speed data. So vibration analysis focuses only on oscillations. And since oscillations translates to frequency domain, so this particular analysis consists of time domain properties, time domain analysis, frequency analysis, and time frequency analysis. So 1 second. So basically, if you look here, the source here is any rotating machine, which will result in some vibrations. And then we have vibration sensor, which could be either accelerometer, piezo sensor, electric sensor, or MEMS, anything, any sensor which can sense the vibration in the system, which will get you the vibration data. Then there will be signal processing step involved, which will do the filtering if you want to utilize only the smaller band instead of working with the full frequency band, or if you want to remove the noise, then all those type of, or the main issue that we faced when we work with the real-time data is missing values and outliers. So all those also will come into processing stage, where you will fill out missing values, and there are multiple ways of doing that. And likewise, you will handle the outliers. Either you remove those measurements or readings from your data, or you refill them using either Z-score or depending on the application and the equipment under study, the correct replacement strategy can be decided. So this missing values, either you can replace it with mean, but mean will be very good if you don't have many outliers in your data. If you have outliers, then your mean value will be biased because of that one outlier value, and which will result in a very weird looking data for you. You won't what I mean by weird looking data is you won't end up getting the information what you have been looking at because of because you have filled the missing values with the mean value, where median could have been the better option. So that's why I said depending on the application and the underlying system, we decide which filling missing value or outlier handling, what strategy is best. Now, for methods, we have three different domains here. One is the time domain, then frequency domain, and then time frequency domain. So time frequency domain plots, we usually call them scalograms if you generate them using wavelets. But if you generate them using short time Fourier transform, then the similar type of plot will be called as spectrogram. So once you deploy any of the methods, then the final output will be your diagnosis and detection. You will be able to tell based on the trend analysis whether the fault or degradation has happened or not. So I will be discussing time domain and frequency domain methods in big detail. For time frequency, because of the time constraint, I have not included it, but I'll just briefly talk about it. What actually happens in time frequency domain. So as we have seen, the signal of interest here will be vibration sensor, but it doesn't mean that you will only look at the vibration sensor. So vibration sensor data you will get in time domain. So you will get the amplitudes or the speed or the displacement, any of these factors you will get. From that, what you will do is you will look at the amplitude, RMS velocity, root mean square velocity or distance or displacement, anything, it could be anything, but the metric or the signal of interest is RMS value here. We can look at kurtosis or skewness, crest factor. All these four are for the time domain features. And then in frequency domain, we have frequency, number of peaks, phase value, and this fault frequency is something, this is a terminology which is very commonly used in vibration analysis. And what it does is it requires no data analysis. Just by looking at the system itself and looking at the FFT plot, there are certain fixed frequencies at which systems behavior can be isolated or segregated. So at these, this BFO is ball pass frequency outer ring, ball pass frequency inner ring. So it is all these things are with respect to the bearing. So in previous, I think somewhere I had mentioned in details, yeah, here, bearing wear. So all these frequencies are associated with the bearing wear. Now, going in details with the time domain features. So as you can see on the screen, when it comes to time domain, there are different metrics or properties, any statistical property that you can use within while respecting the time domain boundaries can be used for the analysis. But these five are some of the commonly used metrics in literature. So the beauty of time domain is you do not need to transform anything or make any change to the signal. You use the signal in the raw form, which is the time domain form. And obviously pre-processing steps are there, but that is not changing the domain of your signal. Your signal or data still remains in time domain. You are just cleaning your data a bit. So the first one is RMS, root mean square. You can think of it as the loudness of the vibration. So what it does is it will measure the overall energy of the system. And whenever the trend or the RMS trend or value is rising over weeks, continuously rising over weeks, then it gives you a very clear-cut indication that machine is getting louder, and which translates to there are increased vibrations in the system or machine, and you something has started to change. Either there is some loose connection, or there is some extra wear, or some wear has started to happen in the bearings. Like any of the things can happen, so it will indicate that. So sometimes the loudness can be heard by humans also. So for example, when we are driving a car, sometimes we do hear the car is making some noise, right? So that means either something is stuck, or whenever there is a noise and we are not able to figure it out, we usually take it to the service center and try to figure out why the excessive noise is coming. So that noise is nothing but something is loose, or something has started to behave as not as per the expected behavior. So something has started to deviate. That's the indication here. Now there are thresholds, standard thresholds, and these thresholds are as per the ISO standards. So if your RMS value in machines is below 2, then it is like normal behavior. And since here we are looking at speed data, so that's why the units here you are seeing as millimeter per second. So it's a speed signal which has been considered here, or the thresholds are for the speed signal. And if it is between 2 to 4, then it means it's an alert zone. Still nothing has happened. This is 2 to 4 is the zone where condition monitoring will come into picture and will be able to segregate normal behavior from the abnormal behavior. And if the value or the RMS value is more than 4 to 5 millimeter per second, then that means the damage has already happened. So this alert phase or the region is our scope or condition monitoring scope. Now the second, coming to the second metric, it is kurtosis. So kurtosis, it's very subtle metric, but it's very, very important. So I hope you guys are aware of the Gaussian distribution, and any Gaussian distribution has certain statistical moments such as mean, variance, skewness, and kurtosis. So kurtosis is the fourth order of moment. What it tells you is the spikeness of the signal. So kurtosis is a measure of the sharpness of your peak. So when you have a Gaussian curve is bell-shaped curve. The sharpness of the curve or the peak is what kurtosis defines, or kurtosis is all about. Whenever the signal is healthy, the kurtosis by default for a Gaussian process, kurtosis is healthy. But if your process is non-Gaussian, then the kurtosis will be either higher or lower. And based on that, we define whether it is, it could be like positive in either direction, positive or negative. Like it could either go below 3 or above 3. So is here the reason why it is assumed that kurtosis 3 acts as a normal behavior or a healthy behavior is because by central limit theorem, it's a very popular theorem in time series analysis or statistical analysis, which says any time series data given enough samples, it will always follow Gaussian distribution. So even though your distribution, let's say, is T distribution today or chi-square distribution today, and you have certain amounts of samples, let's say 1,000 measurements only. But if you collect 1 lakh measurements, then this chi-square distribution or T distribution will look like Gaussian distribution only. So because of central limit theorem in condition monitoring as well, kurtosis value of 3 is considered as a healthy signal, a Gaussian signal. And whenever there is the deviation from the Gaussianity, or the signal is not following the Gaussian characteristics, that's when we say that something has started to, it's a defective component. So whenever there is an default, then that time kurtosis will be greater than 6 or 3 to 6, somewhere between 3 to 6. But if it is a very, very severe fault and the complete damage has happened, that times it will be greater than 10. Usually, whenever it goes above 6, that time people usually start bearing inspection at this time. Now, the next one is the skewness. So skewness is the third order of moment. Again, it indicates, it's a property of any distribution or any time series data, statistical property. Here, what it tells is how symmetrical your distribution is. So your skewness is more about symmetry thing, and for healthy signal it will be 0, because and again this is respecting the Gaussian distribution with the central limit theorem. If it is skewed towards left or right, then that means it is skewed and it is abnormal behavior. So the normal range or threshold is typically 0, which indicates Gaussian behavior. Any deviation from the Gaussianity indicates a fault, but in that case also, if skewness is greater than 0.5, and you should notice that I have absolute value here instead of the raw value. For kurtosis, it was just the value has been considered, but for skewness, since the value can be negative as well, and it doesn't matter to us whether it is in the negative side or the positive side, whenever the value is greater than 0.5 on either side of the spectrum, then it means it's a starting of the fault or the our area where we should focus. But if the skewness is more than 1.5, then it means the fault has already happened. So again, we should target or focus on the middle range here, where whenever it is above 0 and less than 1, that point or that space is the scope of condition monitoring here. And it should be very evident from this thresholds that if your skewness is increasing, that means your fault levels are increasing. Now the next one or the next property is the crest factor. So crest factor, it's a combination of the peak amplitude and the RMS. So if you look at the mathematical formula, it is nothing but the peak amplitude divided by the RMS value. And it captures isolated shocks. So what happens is when your crest factor is very high, but your RMS value is low, then it is a classic early fault signature. So a very few sharp impacts, but the overall energy will still remain low. So so just by comparing this, basically what I'm trying to say is if your peak amplitude is high, but your total RMS overall energy contribution is low, then that means it's a faulty signature. Something is not correct in your data. Your overall energy is low, but the peak is very, very high. And likewise for this also, if your crest factor is falling within the range of 2 to 3, then that means it's a healthy signal or healthy component. But if it is 4 to 6 or higher than that, then it means fault has already happened. And again, the scope lies between these values. So this I already mentioned, if your crest factor is high, RMS value is low, that means you can identify the fault early and you can stop the damage from spreading. Now the next value here is peak to peak value, which is nothing but you just take the maximum peak value and the minimum peak value and use that as the metric or feature in your analysis. So this this is a indication of structural displacement. It will indicate if there is a clearance, physical clearance or tolerance limits are being hit, then it will indicate all those scenarios. And here the thresholds are very specific to machines. There are no generic thresholds, and the thresholds are driven again by the same standards, but it is very machine specific. Only thing is, or only concluding remark on this peak to peak value is that if the value is exceeding the threshold, then that indicates structural risk. So in all of this, the underlying idea is irrespective of what metric you use. For each metric, you will have a certain threshold, and whenever the value exceeds the threshold, that's when you start to say or you figure out that something has started to change in your system. The threshold should be set in such a way that it should indicate the normal behavior or the healthy behavior. If we set it to the healthy behavior, in that case we will be able to work in this alert or alert zone where fault has not still happened, but it will happen within some time. Given some time, it will happen. So this is the scope of conditional maintenance monitoring. The threshold should be set very carefully in any of the condition monitoring technique. So here is the example which I was talking about. So here I have taken a bearing data. This is the time series plot, just the amplitude. I have not converted or calculated any of these metrics, just the time series amplitude plot I'm showing. And with this time series plot, I have calculated all these metrics which I just discussed for the healthy bearing data. Now there is a fault which has fault has occurred, or it was instilled in outer race, inner race, and ball. All the three places there is a fault. Some wear and tear has happened. As you can see, the second plot here, it shows when the fault has not completely occurred. Matlab, it has just begun to start. So the same signal, just look at the way it has started to change. You can very clearly observe these oscillations, increased oscillations at a certain period, at a fixed, it looks like it's at a fixed interval or period. So this was not visible in the raw data, in the healthy bearing data. But if you look at a completely faulty, severe faulty bearing data, then it is very, very evident. So there is a fault which is resulting in high oscillations in your signal. So time domain, in time domain analysis, what we usually do is just by looking at the visual inspection, or the visually looking at the data, and then tracking some metrics or statistical properties, comparing them with thresholds, we will be able to identify the faults. So if you see here, this 0.5 line, it was just marked for the comparison purpose. But here, if I set a threshold of, let's say, 1.5, then I'll be very easily able to figure out that these oscillations I will miss out, because it is riding on top of the time domain characteristics. So I will miss out on those. But somewhere where when there is a high peak, I will be able to pick that and able to tell that something weird is happening in my system. And here I'm just showing how the metric changes with the fault progression. So when fault is less, there is no fault. All the four metrics are very low, but as the fault percentage increases, where 100 indicates the severe fault, the maximum, the component has completely damaged. So as you can see, all the metrics starts to rise in value. So that's all about the time features. Now, are there any questions on the time domain analysis? Okay. So the reason I highlighted or pinpointed these oscillations, which are very clearly visible here, is it's the motivation, because this is not always the case. There are times when you have so much noise in your data. So for example, this particular data, you can't figure out what is happening, or if there are any oscillations because of fault. Every up and down is an oscillation, but whether that oscillation is a normal behavior or due to fault, that thing is not very clearly visible or indicated by this time series plot. So that's where time frequency analysis or frequency plots come, FFT plots come into picture. So if you convert this into FFT domain, and if there are faulty frequencies, or the frequencies at which or there are oscillations due to faults, so that will be very clearly visible in your FFT plot. So FFT plot, what it does is, or frequency transformation, what it does, it transforms your time domain signal, converts it to a combination of sinusoid signal, which is sine theta and cos theta. So it's like a very beautiful way of representing the same information in terms of frequencies, and this transformation allows you to pinpoint or figure out the fault very clearly. So for this type of signal, where it's very difficult to say or find out anything, in frequency domain, it's very evident. We have 4 peaks, and these BSF peaks are nothing but what we discussed here in the time domain properties, these fault frequencies. So these are like deterministic frequencies. It's very easy to calculate that. If you want to know more about it, I have a backup slide on this, so I can show you that. But the point is, things which gets hidden in time series plot or time series analysis because of presence of noise gets highlighted very clearly and beautifully in the frequency domain. So that's why frequency domain analysis is also equally important. And just a kind of a reminder that all the data or the sensor data what is being used is the vibration data. So even though we have moved from time domain to frequency domain, we are still using vibration sensor data only. So here also few steps are same. We have data, we pre-process it, and then we take the fast Fourier transform. We do the Fourier transform. Now there are different ways of taking Fourier transformation. You can either do discrete Fourier transformation or fast Fourier transformation or continuous Fourier transformation. Again, that's a huge topic, and I have not covered that here. So, but FFT is the most commonly used because it works very well with the practical data or the real-time practical data what we get from the actual machines or vehicles. So that's how, so this is the formula that converts your time domain signal xt, which we just saw here. So if you represent or you notate it as xt, then using this formula, you can convert that signal to this spectrum. So this is nothing but your XF, the transform signal what you are observing. And when it comes to frequency domain, in time domain, we have looked at the kurtosis, skewness, all time domain properties. Likewise, in frequency domain, there are certain properties, peak amplitude, power spectral density, spectral root mean square, modulation index, all these properties, total number of peaks. So multiple, anything in the frequency domain, which can act as a feature, we can extract that and then again compare it with threshold and detect the fault. If no fault, we keep continuing monitoring. So before going into the example or the details of each of these metrics, what I want to highlight is your time domain metrics will tell you if a machine is failing, but it won't tell you when it is failing. Or what frequency analysis allows you, it will allow you to have a very targeted prescriptive maintenance. So you will be able to segregate two closely occurring faults, which you might miss out in time domain because of the closeness of the faults which are occurring, or because of the presence of noise. But you will be able to segregate those very nicely in the frequency domain. So time domain techniques or approaches are best suited for repeating and impulsive faults, whereas your frequency domain techniques are more suited for the discrete and harmonic faults. Because harmonic again is associated with the frequency, so it becomes a bit easier to segregate those things in frequency domain. I think we don't have that much time, so I'll skip going through each of these points in details. But here, what we are doing is, again, we have a threshold. We look at the so for example, if you look at this particular plot, this is your peak frequency, and this peak frequency amplitude you can use. And then you have spectral RMS. Spectral RMS is nothing but you basically look at the power which is concentrated in a very limited or shorter band instead of looking at the overall power. So if you sum each of these values, then that's what you will get PSD, so this plot, what you are seeing here is the power spectral density. So one of the metric that can be used is the PSD itself. And both in time and frequency, we can use windowing techniques where we can use, instead of using the entire signal at the same time, we can use a smaller window and look at the metric in that particular window in order to track whether it is exceeding the threshold or not. And that way we will be able to pinpoint where exactly the fault has started to happen or the fault has system has started to deteriorate. And then we can also look at the sideband energy. The sideband energy is nothing but, if you see, so here the green one is the healthy and the red one is the faulty. So in green one, these are for the same component. But if you see here, the red and green are kind of coinciding at this particular frequency. But later on there are no peaks available in the healthy signal, whereas your faulty data has multiple peaks. So these are called as side lobes. So apart from the main component, energy component, which is present in the signal because of the intrinsic nature of the signal, there will be some additional peaks which are due to the faults. So that becomes very easy in frequency domain, and we can use that as one of the metric to identify the faults. So for the same data, if you look here, what we looked at the time domain in the time domain slide. If you look here, this is the side lobe or the sideband energy for your healthy signal, where everything is like very, very low. It is less than 0.012, and there are no peaks. So this variation, what you see, is because of noise in the data, and it is in any real-time data, this will always be the case. Whereas in the faulty data, in the same frequency range, you can very easily see. So if you see this place where when there is or the frequencies at which the fault is not there, your energies are very similar to what you are observing here. It is less than 0.05 here, and which it should be mostly around the same thing. But there are some frequencies at which you have very significant or dominant peaks, and that indicates the occurrence of the fault in the system. Now, here I'm comparing the same thing, but with the spectral analysis also. So, what we do in spectral or time frequency analysis, we combine both the time domain characteristics and the frequency domain characteristics into the same technique, and that's what we do it in time frequency. So when we work only with time domain we miss out on the any of the frequency features. We cannot segregate two closely occurring faults or in presence of huge noise. Those segregations become difficult. Whereas in Fourier in frequency domain, you will be able to identify how many faults are there, but you won't, since you don't have the time information here, you won't be able to figure out when it has occurred. Only thing you can tell is whether this data has faults or not. So time frequency analysis combines both. What it will tell you in each segment of data. So it retains time resolution as well as the frequency resolution. It will tell you how much energy is concentrated at what frequency. At the same time, it will also tell at what time. So here you can only see at what frequency how much energy is there. There is no time information. But here you can see the color here indicates the intensity or the magnitude of the frequency, magnitude of the energy. So here you can see, if I pick at like this particular dot where my cursor is. So at 200 hertz, at this time around maybe 5 milliseconds, my energy is red, and usually I missed out on the power indicator, but this much energy is there, so that information can be extracted from this. So both time and frequency thing can be extracted, and all three of them have their own benefits and drawbacks. So we should look at the system and the underlying system and figure out which technique will work best under what scenario. Moving on to the data-driven analysis. So this data-driven analysis uses machine learning algorithms to classify faults, detect anomalies, and predict the remaining useful life. So this remaining useful life prediction part is a part of predictive maintenance and not the condition monitoring. But the reason I have included is the same model or the same approach can be used. Only thing is the objective needs to be changed. In condition monitoring, we only focus on classifying and detection. In predictive maintenance, we focus on all three. So that's the difference, and that's why I have just included it here. And all of this will be purely data driven without any explicitly explicitly including the physics or the system behavior. So only data driven approach, and no physics is involved here. What the flow, if you look, more or less it is same only. You have source. Now, like I said in the beginning, here the source can be any sensor. It is not restricted to the type of the sensor. Any sensor can be used. Sensor data, then we do the feature extraction. We extract whatever features are most suitable for the fault type of system we are handling. And then we train our model, we train any machine learning model with the selected features. Based on the training, for every new upcoming data, we make the prediction. Now that prediction, either it could be for the anomaly detection, or it could be for classifying whether classification problem. And this is the prediction, predictive maintenance. So I'll ignore this one right now for now. So we can detect or classify the faults there, and based on that, we can take the necessary actions. Now, these are some commonly used machine learning models which are there or which are widely used across different industries. Regression, how much time I have? Okay. So again, I won't go into detail of what each of these model does, but what they will do is each of these modeling technique has a type of features for which it works best. So for example, if you have a huge amount of data and you have like same data from 10 different sensors, but since you have 10 different readings, that does not mean you have 10 different features. You have only one feature but 10 different ways of collecting it. So let's say I have speed, velocity, and distance, and I'm using them, all three of them, as my features. So what PCA will do is PCA will figure out for the problem statement at hand which feature is more relevant, because all three of them are giving more or less underlying information is more or less same. The time is fixed, and your distance will drive the speed, and so it's like same redundant information. So but that's what PCA will do. PCA will reduce your dimensionality. Clustering will allow you to segregate or classify it into two different classes. It will create a different clusters based on different techniques, but commonly used or most popular ones are k-mean clustering and db scan clusters. Time series, you just forecast the future behavior based on the previous trends or the historical data. So like this, all these are the commonly used, but the most interesting of this is, I personally feel it's very interesting, is the hybrid ML, where you combine so there is something called PNNL, which stands for physics-based neural networks. What it does is, neural network are purely data-driven, but physics-based is you include certain aspects of the system behavior or the underlying physics, and then you combine that with the data driven approaches, so you capture both the physics of the system as well as the data. So these become type of techniques become very powerful for certain use cases or certain systems. However, it could be overkill for a very basic problem. A very most commonly of them are regression analysis, which is like widely used in industries. So for the same data, here I'm just what we saw in time domain and frequency domain. What I'm showing here is the clustering output. So here you can see we have three different types of failure faults, and then we have the normal behavior, and all three of them are segregated very clearly as compared to the normal behavior using k-mean clustering. And here I'm showing the comparison on the same data, the performance comparison of different models, what I just showed in the previous slide. So support vector machine, random forest, KNN model, CNN is neural network, and then LSTM. So different models are the performance is shown here. So this is just to highlight not every model works best for or works good for every scenario. Depending on the use case, this underlying system, we have to do a trial and error and figure out which model works best for this particular problem statement. It cannot be generalized. Out of this, we need to figure out which one is the best suited for our problem at hand. And then only we'll be able to make a more accurate prediction or classification. So that's all I had for the techniques. Now coming to how do we decide when to choose which approach. So if you have a bearing rolling bearing component, Then there the common fault is fatigue or spalling or wear and tear, and it's rolling bearing, so there is a lot of vibrations that is happen. So vibration analysis are the best suited for this type of components. If you have electric motor, so electric motor, you will easily get current and voltage signals. So motor current signature type of techniques are best suited for motors. For gearbox, if you look at a gearbox, FFT or acoustic emissions are best suited. And likewise for hydraulic systems. So wherever you have some liquid to deal with, oil analysis is the best, because in systems mostly it's oil or some lubricant only. So oil analysis specifically looks at those type of problem statements, or finding out faults or wear and tear where oil is involved in the component. Engine or powertrain, thermography or vibration works very nicely. And for structural part, acoustic emission or ultrasonic, any of the techniques can be, either any of these two techniques can be used. So the major key takeaways from today's talk will be, we should understand that condition monitoring is a preventive intelligence. It is here, the goal is never to fix a machine or to fix anything. The goal is only to figure out when things starts to change and take the action at the beginning of the change so that the fault doesn't happen. So it's a preventive approach. There is no technique in literature that works for all type of faults. There is like nothing that works for everything. Vibration, even though it's highly or most widely used, it also works very well for only a specific set of components or machines which involves vibration in it. If you go ahead and use a vibration approach for your, let's say, electrical motor, then you might not end up getting very good result, in the sense that you might not end up identifying the fault early. So, but if you implement, or if you implement any electrical monitoring strategy or technique, your accuracy of the model will be very high. And like I mentioned this in the beginning, when we started to discuss on the techniques, the condition monitoring techniques, AI, ML, it is not replacing any of the domain knowledge. There are techniques which works very well only with the dedicated sensors, but the AI, ML is something which cut across all the domains, and hence it can be combined with any of the approach, such as vibration analysis, oil analysis, electrical monitoring, electromagnetic monitoring. It can be used with anything. It is not, you do not need to know the domain in order to use AI based strategies or data driven strategies. Now, this one is specifically, since we have discussed vibration in details. So, therefore, the fault frequencies, which are very common, and these terminologies are very common in any CM or fault CM technique, especially vibration techniques. So we should be, these are theoretically calculated frequencies for each machines. So we should be aware of these frequencies when we are working with the vibration analysis. Any spike at any of these frequencies indicates there is a fault in the system. And signal processing is the key, or it's the heart of the overall approach. Raw sensor data is very noisy, even though you have right technique, right sensor. But if you skip signal processing step and don't clean your data, you will end up getting lower accuracy. Again, this one is for the vibration analysis, that time domain features will tell you severity, whereas frequency domain feature will able to identify different faults in the system, which you can't do with the time domain feature. Time domain feature, you can only figure out whether the fault is there or not. Frequency domain will allow you how many faults are there. And this is kind of my personal key takeaway for you guys, that data without context is just noise. You need to know your data you need to use data properly in order to extract any useful information. If you don't have any context of what the data is about, then irrespective of how good data you have, if you don't know what to do with it, it is just noise and it won't be useful at all. That's all I had. If there are any questions, I would be happy to take them.
No, sir.
Thank you, ma'am. Thank you. Okay, actually, two questions have been asked in the chat box, ma'am.
Okay, I will check one second.
Yeah.
For condition monitoring of VCR emission, which is operated with alternate fuel for its vibration, performance, and emission, which AI tool can be used. Since it's engine, so for engine, there could be some vibrations as well. So you can use a combination of vibration and performance for the VCR engine. It's again, when it comes to like vibration and performance, you need to figure out the right technique from both of them and then combine them correctly. It all depends on what type of fault you are looking at. So you can use a combination of both. For analysis of DC motor machine, vibration analysis is better or mostly DC motor. So for you should always start with the time domain because time domain, without doing the time domain analysis, you won't be able to figure out whether how much noise is there or whether time domain is useful or not. Once you feel that time domain is not suitable or you are not able to extract or identify the fault with that, then you should move on to the frequency domain analysis. But in vibration, for example, for this bearing example, there are certain frequencies which will indicate very clearly, and these can be theoretically calculated. So for those type of faults only, you can directly jump to frequency analysis. But otherwise, you should always start with time domain analysis and then move to frequency and then time frequency. Are there?
Thank you. Dear participants, if you have any queries, kindly post it in the chat box. Otherwise, you can unmute yourself and ask your doubts if you want to get clarified. Thank you, ma'am. Thank you that nobody has raised any questions. And okay, thank you, ma'am. That's a presentation. Okay, really the session was wonderful and very informative. Okay, thank you very much for having spent your valuable time with us on this happy occasion. Thank you, ma'am. Thank you very much on behalf of Department of Mechanical Engineering, Knowledge Institute of Technology. Thank you.
Thank you. Thank you. Bye-bye.
And yes, ma'am. Thank you. Dear participants, you have an announcement. Okay, the next session will be at 12 p.m. So next session, you have half an hour break. So the next session will begin at 12 p.m. Mr. Danam Tilak, who is the head of standardization from Titan Bangalore, will be the resource person. He will be addressing us on IoT integration for smart machines. So kindly join the session or be in the session, which will begin at 12 p.m. this month. Thank you.
Hello, sir.
Hello. Yeah, am I audible?
We are not able to hear you, sir.
Hello. Am I audible now?
It is very low.
Hello.
Yes, sir. Mildly only we are able to hear you, sir.
Can you check now? Is it any better now?
Yes, sir. We are able to hear you, sir, but it was little bit milder.
So even now it is the same way.
Okay, sir.
Is it better now? Can we continue like this or?
It is somewhat better than previous, sir.
Is it better now?
Yes, sir. Yeah, now it is well good, sir.
Okay.
Okay. So we will start in another 2 minutes, sir.
Sure.
If you want to check if you want have any presentation, means you can share it, sir. We can check whether it is able to see for all the audience or not in between the meantime. Yes.
Is my screen visible?
Yes, sir. Screen is visible, sir.
Now?
Yes, sir. It is visible, sir. Visible. Now it is. F5. F5. You can press
Yeah.
full screen. Okay.
Okay. Please let me know when we are ready.
Yes, sir. Yeah, another 2 minutes we will start, sir.
Sure.
Okay, shall we start, sir?
Just a minute. Just a minute.
Okay, sir. Okay.
Yes. Can we start?
Yes, sir. I will give the formal welcome for its user.
Yes.
Yes. Good morning to all the participants. It is my privilege and honor to introduce today's distinguished resource person, Mr. Danam Tilak. Danam Tilak is head of standardization at Titan Engineering and Automation Limited, TEAL, a leading organization known for its excellence in engineering and automation solution. He has an extensive industry experience in manufacturing system, standardization practice, process improvement, and energy engineering management. Mr. Tilak is also a proud participant of Titan's prestigious Emerging Leadership Program, which recognizes and nurtures high potential leaders through a mentorship, industry expos, leadership master classes, and strategic learning experience. His leadership journey has been widely appreciated by the colleagues, industry professionals for inspiring guidance and professional excellence. Today, he will be sharing his valuable insight and practical experience on the FDP topic, which will be undoubtedly benefit all the participants from the academic and industry. On behalf of Knowledge Institute of Technology and the FDP Organizing Committee, I extend warm welcome to Mr. Danam Tilak and thank him for accepting our invitation to address the gathering. Ladies and gentlemen, please join in the welcoming and the esteemed speakers. Over to you, sir. Thank you.
Thank you. Thank you for your warm welcome. Hope I am audible and my screen is visible.
Yes, sir. Yes, sir. Sorry, please.
Okay. Good morning, esteemed professors. So I'll just be so I am a generalist and I am not a specialist like you guys. I am a generalist, but I have uh, domain knowledge on all the verticals that entice in the IoT integration part. So I'll be taking this session from that angle, and I'll try to embed how and what are the exact requirements from academia for industry as far as IoT systems are concerned. So that would be my focus area and the challenges. So I will not be going through the uh, regular architectures which you have all seen for past 10 years. So you are all veterans in that. That is why I'll not be touching on that. What I'll be focusing more on is the challenges that we are facing. How do we address that with both industry and academic collaboration? Things like that will be my focus area for this particular session. If that is okay, and if the setup that we'll have the session for 75 minutes from my side, and at the last 15 minutes or 70 minutes of my session and last 15 minutes Q&A, if that is okay, we'll proceed now. Can we go ahead?
Yes, sir. You can go ahead, sir.
Okay. So I'll just start with a brief introduction of my organization. So if you see, there is, so I am part of Titan Engineering and Automation Limited. Titan Engineering and Automation Limited is a wholly owned subsidiary of Titan, which you all know. So this started out as a small maintenance team in the Titan watches factory when there was an embargo placed on India of importing machines from Switzerland. Watches maintenance team brought together like-minded people who wanted to develop their own assembly lines. So in that way, a small team formed which was passionate enough of building assembly lines. And these particular individuals started building assembly lines for watches. So if you know about the watch manufacturing story, it requires very high precision, minute parts inside it. So we gained our expertise in building such assembly lines. And at the 1990s, mid 1990s, we exhausted the requirements within the watches division, and there was a need felt that this is a unique skill set, and this skill set can be used by giving the services outside the Titan ecosystem to other customers also. So that is how a separate division within Titan formed, named as Precision Engineering Division, and they started giving out machines to auto OEMs from 1994 and 1995. Slowly so that is how our journey started. And then within 2-3 years, there was another subdivision within Precision Engineering Division which started manufacturing precision components for aerospace and defense. So these two verticals formed within the Titan Engineering and Automation Limited, and we started serving multiple customers, both domestic and export. And within some 10 years, our revenue split was 50-50. That was, we were serving 50% domestic customers and 50% export customers, which is a feat for us, which also shows our focus for quality and our focus on innovation. And in 2017, we formed as a completely separate organization, which is a wholly owned subsidiary under Titan, and that is how the TEAL came into existence. So as I said, there are two verticals, which is automation solutions and manufacturing solutions. I am representing automation solutions today, and I'll be talking about the topic IoT for smart machines in the context of automation solutions business. So this is about the organization that I come from, and before starting, I'll just take a brief introduction about me. So my name is Danam Tilak, and I have nearly 10 plus years in the industrial automation field. I passed out from IIT Madras with a dual degree. After that, I joined TEAL. At that time, it was PED. So I was a mechanical machine designer, and then I entered into the standardization team. So so the switch from the machine designer to standardization team was a pretty significant one for me, because as a machine designer, I was solely focused on creating 3D and 2D, and then focusing on DFM, GD&T, things like that. But after a point of time, I felt that we as designers were doing multiple repetitive activities which we wanted to automate. So that is why I switched into a separate team which builds parametric models for CAD models, and also builds productivity tools on top of CAD softwares. So I made the switch to design standardization team, which deals with automating mundane but essential designer tasks to improve the productivity. So soon I started taking care of both design as well as process standardization, where I was also looking into business excellence initiatives. And this helped me understand the amalgamation of mechanical, electrical, and IT systems much better. So this is when I started to understand the entire IoT ecosystem, the digital twin ecosystem, and virtual commissioning ecosystem. So with these, when in my stint as a design and process standardization team, I successfully implemented a pilot project for the virtual commissioning that was established by the organization for the first time. And then I became the program manager for the entire standardization activity, cutting across mechanical, electrical, programming, all these verticals. So as explained, I am part of the leadership, an emerging leadership program from Titan, and I am also a TBM Gold Assessor. So TBM is a internal business excellence audit that Tata Group does for its own group companies, and it selects very few individuals within the management cadre as assessors. So I am part of that pool as well. So with these introduction, I'll start the actual session with which we are gathered here for. So smart machines. What do we mean by smart machines? And are smart machines just a jargon? We start with this introduction and we proceed further. So if you see the my understanding of smart machines is any equipment which is AI or ML enabled, which has advanced connectivity. Here I'm not talking about internet connectivity, I'm just talking about connectivity within the machines. And it has the capability to execute informed decisions without any human intervention. So this is the more or less the standard definition of a smart machine that everyone can go across. And as you all know, there are 4 layers of the architecture which goes into building of a smart machine. There has to be a layer which senses, there has to be a layer which connects, there is to a layer which thinks, and there is a layer which actuates. So this is the basic framework of smart machines. Now, why do we need integration of IoT? So if you see, the smart machines integration integrates with industrial IoT, and it forms something called as cyber physical systems. So these cyber physical systems are a complete different ball game, where we stop just activities what we used to do with SCADA, and we go to a one level above for governance of the each and every machine that is present in the shop floor at the fingertips of the management, so that the informed decisions can be taken quick. So this is the context with which we move ahead. These are this there are smart machines, and once you amalgamate smart machines with IIoT, which is industrial Internet of Things, we get something called as cyber physical systems. Now, why is cyber physical system important? Because let's be honest, there are multiple initiatives that are undertaken within everyone's organization, where it is done as a marketing gimmick, just to show that we are doing cool things. Many initiatives are undertaken. Is smart machine just a buzzword? Is a cyber physical system just a buzzword? To understand this, let us go through a case study of Rolls-Royce Total Care program. So, can I get a show of hands if anyone of you has heard about this Rolls-Royce Total Care program? Hello? Hello, am I audible?
Yes, sir, you're audible, sir.
Can I get some show of hands if anyone knows about the Rolls-Royce Total Care program?
In chat box, they said you have replied, sir.
Okay. So, even before IoT was a thing, Rolls-Royce made their own version of industrial Internet of Things. So, as you all know, Rolls-Royce builds aircraft engines. Rolls-Royce completely changed the game of the aircraft engines by investing in their own stack of Internet of Things. So, if you see, Rolls-Royce has one control center sitting inside UK, which keeps getting data from each and every aero engine that it has supplied all across the world. And they completely flipped the game, saying, we will not charge you for spare parts. So previously, the problem statement for all the aero engine companies was, once an engine breaks down or it comes for maintenance, they change spare parts, and they ask the companies to pay for those spare parts and the maintenance activity. Rolls-Royce completely flipped the game. They said, how many hours our engine is in air, you pay us for that. So Rolls-Royce took the complete ownership of making a engine in air onto themselves rather than giving it to the customer. They were able to do this because they were in a position to create a successful IoT setup within their aircraft engines. So the architecture that they used for it was, there is a sensor data that keeps coming from engines, and it was sent onto their onboard computers, and there was edge computing, the like very basic version of edge computing that they did, and then that data was sent to the satellites, and via satellites, the data was transmitted onto their R2 data labs, which is the Rolls-Royce's control center for the aircraft engines. And then these data was fed back to the predictive maintenance teams on the shop floor, who were deputed onto the aircraft operators, who used these data to analyze and maintain the entire engines, so that the operator as well as Rolls-Royce team, they got the maximum benefit of the technology that was available. So even before internet became a thing, Rolls-Royce was successful in establishing the IoT architecture within the existing technology that they had by using satellites for their data transfer protocols. So this is what is considered as the birth program for Industry 4.0 and Industry 5.0 systems. And these formed as a benchmark across the world on how to establish IoT, and not just establish IoT for the sake of looking cool or showing good dashboards, but deriving actual business value out of it. So again, coming back to the context that we have set for ourselves, is CPS just a buzzword, or is it actually driving business value for customers? So this is a clear example which states that even without the advent of the advanced technologies which we have in our toolkit at the moment, which is, let it be cloud computing, be it AI, be it ML, be it 5G, without any of these technologies, they had a very clear business case, and they implemented and they innovated, and they gained huge market share out of it. So this is one such example. And then there is another example where, as all of you might have heard, that many factories get ISO certifications. They get like Deming, they challenge for Deming prize, they challenge for AHQC's prizes. So factories do all sorts of things to show that they are committed for some vision that they have. So if a factory is challenging for Deming prize, and if they are successful in that challenge, that means we know that they are a completely TQM adherent organization, where there is a clear focus of quality across business value chains and ecosystems. In a similar way, McKinsey company, with the association of Economic World Forum, they started handing out lighthouse factory badges for multiple factories within the world. The criteria for this is very stringent, and only when these criterion are met, they will award your factory lighthouse factory. So can I get some engagement from the participants? Have you heard of lighthouse factories, or have you known any lighthouse factories? Hello? Okay. So right now there are 20, approximately 20 factories in India which have been awarded Lighthouse Factory brand, and there are nearly 200 factories across the world which have been awarded this tag of a lighthouse factory. So this is part of their lighthouse program that they are running to make multiple manufacturing organizations across the organization ready for Industry 4.0 and Industry 5.0, because the Industry 5.0 deals with human machine collaboration, and we cannot reach industry 5.0 without being industry 4.0 compliant. So this is the program that the McKinsey guys have taken up to grade multiple factories on their readiness of industry 4.0, and have they set a benchmark in that. So what do they see? As always, CPS, IIoT, they are no longer buzzwords. If you are not able to show clear, measurable business impact, it is just a marketing gimmick, and it is outright rejected. And you have to show strong use of advanced analytics and AI, and you have to show the integration of those processes within the daily work processes and key work processes within the organizations. And you have to establish the IT-OT convergence. So what do I mean by IT-OT convergence? IT is information systems, uh, uh, information technology, OT is operational technology. So operational technology is PLC, SCADA, these softwares, and IT is ERP, MES, these softwares. Generally, both these softwares are siloed in nature, so they don't talk to each of them frequently. But the base requirement of Lighthouse Factory is an IT-OT convergence. For example, it is very recent phenomena that we have started integrating CAD and PLC software by doing virtual commissioning and by doing digital twins. My esteemed uh, co-presenters who were presenting before me on basics of digital twin might have covered this, but just for the context, I'm just setting it up again. So if you see, there is mechanical CAD, there is electrical CAD, and there is PLC that is governing the entire control logic of these machines. So I am talking again in the context of Titan Engineering and Automation Limited, where we build SPMs or turnkey assembly lines. So for us, these data were in silos for the longest time that I have ever known. Only recently have we seen the advent of virtual commissioning softwares, where we were able to club these three siloed data and drive huge business value out of it. So we were able to crash the entire commissioning timeline by 3 to 4 weeks, which is a huge cost saving on top of our overheads, on top of our manpower costs, and on top of our rework costs. So this is just the direct cost. The indirect cost of quality is immeasurable. For example, if you are a PLC programmer who is sitting in shop floor and you are waiting for an entire assembly to be, or a machine to be built in front of you, so that you can burn your PLC logic into the machine, and only then can you test your logic if it is working well, if the sequence of operations is working well or not. That entire system was uprooted altogether, and the machine was available to the PLC programmer even before the machine got assembled. The machine is available to the PLC programmer 100% of the time, irrespective of machine going for rework. Like few sub-assemblies inside a machine, if they go for rework when the assembly is happening, PLC programmer has to stop the commissioning work again. So these were the challenges which we were able to build only by focusing on the first part of smart machine. We did not even go into the digital twin. We were just able to build a successful digital thread which brought together data from siloed systems who were not talking to each other at all. So this is the IT/OT convergence that the people are speaking about. I am just giving you a single example. If you go look at the actual examples of factories who have won the lighthouse factories, they have successfully integrated MES systems, PLC systems, digital twins, and they have formed a very beautiful layer of applications which will give them business insights real time. And the next focus was workforce upskilling and strong, as I said, building strong end-to-end digital threads. So when I say workforce upskilling, it is not on the work processes. It is on metrics like how much of your workforce is digital ready. How many of them know BI tools? How many of them know what is AI capable of? What are the pitfalls of AI? What is an ML? What are the pitfalls of an ML? What is cloud computing? So these are the dashboards that the organizations are maintaining even for the shop floor level teams to establish the digital readiness for the entire factory and the organization as an extension. So by looking at such metrics, the Lighthouse Factory Awards are being awarded by the World Economic Forum and the McKinsey teams. So, Tata Steel Orissa was the first factory in India to get awarded this particular Lighthouse Factory Award. And they have been a benchmark across Tata Group companies for this particular coveted title of a lighthouse factory. I'll just pause for 5 minutes to check if there are any questions until here. Can we move ahead or? Are there any questions or can I proceed? Hello?
Participant, you can unmute yourself and you have any queries, can ask, or you can put in chat box that you are aware of that.
Hello?
Yes, sir. We can move on.
Okay. So with this as context, so now we have established that IoT systems, CPS systems, they are no longer just buzzwords or marketing gimmicks. They are solving actual real life problems. They are solving factory shop floor problems in real time and deriving business values for the organizations in a, a scale which has never been seen before and it has never been heard before. So now if we with this context, we'll see how can machines become smart. So we have established that machines need to be smart, assembly lines need to be smart, factories have to be smart. So what do we do? Do we directly start attaching sensors and establish communication protocols across them? I beg to differ there. Always we have to start any activity by understanding what is the business use case. Why do you want a machine to become smart? You cannot be generic. I want better OE, I want high cycle time tracking. So these are all generic terms which will not serve any specific purpose for the customers or for the end users. What exact case are you focusing where you need the machines to become smart? What is the business use case? What is the business value proposition? What is the return on investment? I'm not saying that for every R&D endeavor, look at whatever is the return of investment, and only this particular money is being invested, and this has to be extracted back. So if this is the definition of return of investment, I'm not for it. What I'm meaning by saying that understand the business use cases, we have to be very clear on what exactly are we going to gain out of this particular endeavor of this particular project. It cannot be that I'll get a good dashboard, I'll get a good pie chart or a good histogram where I'll be able to get the message on my mobile. What business case it is solving? Based on that, you have to go and understand what data points have to be captured, and then what KPI will be strictly monitored. Only when we are clear on these particular metrics do we actually start a project. We cannot be generalistic and say, I want a IoT system, I will build an IoT system. No, that is not going to yield results in long term. Once this has been established, what architecture are you going to prefer? So I'm sure all of you have heard what is an edge architecture, what is a fog architecture, and what is a cloud architecture. Can someone in the chat uh, please just with raise of your hands, can you just tell what is an edge like, do you know what is an edge architecture is, what a fog architecture is, what a cloud architecture is? I'm trying my level best to keep this engaging session. So that is why I keep asking, like, because this has to be a discussion and not another training session, which you guys are well versed with, which you guys keep taking semester after semester. So I just want this to be a discussion where both you as well as me will gain from this exchange of knowledge. So that is why I keep asking, like, what are your views on any particular thing?
Hello. 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 I am audible.
Yeah.
Sir, I think age architecture is a where we have a data processed in the IoT sensors, not in the cloud.
Correct.
Sir, I have a little bit knowledge about age.
Okay. And fog and cloud? So edge is straightforward, cloud is straightforward. So when we see there is edge architecture, why was there a need for edge architecture? Because cloud architecture is the benchmark. Every data has to be stored from each machine in the cloud, and that will run historical data analysis. It will run multiple AI ML models and give you data. Why was there a need for edge architecture or fog architecture? So here there was a use case where we wanted to implement a system for one of our customer, where for a machine the cycle time was somewhere around 2 seconds. So for every 2 seconds a component was coming out of the machine. But what happened was they tried implementing an IoT architecture for the first time. So what actually happened was the process got executed within 2 seconds, and we were waiting for 2 more seconds for the data to travel to cloud and come back. So because the architecture was not designed effectively, because it was both the consumers as well as the teal's first time of executing a teal architecture, we did not think properly on the architecture, and we ended up doubling the cycle time with no proper root cause itself. So just because the data is going to cloud and coming back, it was taking 2 seconds. Even though the mechanical processes which are supposed to take longer time, they have executed their process and the machine is sitting idly for 2 seconds because the data did not come back. So that is when we started exploring more into the literature, and we understood the terms like, oh, there is something called as edge architecture, there is something called as fog architecture, and there is something called as cloud architecture. Only then we started to understand that IoT is not a simple game where you just add intelligence on top of sensor and say, yes, we have executed an IoT project. There is a lot of architecture design that goes into the successful implementation of IoT projects within a machine. So then we understood the importance of edge architecture, where we need not send each and every data to cloud, and we can localize the decision making architecture uh, and send only the anomalies or send a batch data into the cloud for effective utilization of bandwidth and the network constraints. So what is fog architecture? Uh, all the professors here um, already have had multiple discussions on IoT. I just wanted to know your view on what is the difference between a SCADA system and an IoT system. Is there any difference, or are both the things solving the same thing? What is the difference between a SCADA system and a fog architecture?
Sir,
Hello, am I audible?
sir, SCADA, yes, sir, yes, sir.
Yeah,
Sir,
please.
SCADA is the device which is used to monitoring and control the industrial processes.
Okay.
And IoT, maybe a connecting device. Used
Both
in
are the
daily-
same.
Yes, yes.
So is SCADA IoT, or both are different and they are trying to solve some different problems?
So both solve different problems. Like SCADA used in monitoring and controlling of power plants, but in IoT we are just using fitness tracker or smart homes or smart machines. These are the things used in IoT. I think.
So the SCADA system is only used for extracting data and um, uh, um, running if else logics. So there are deterministic logics that are fed into SCADA systems, and they will be running on according to those deterministic algorithms and execute uh, tasks based on those if else logics. There is no additional intelligence built into the system of a SCADA system. But if you look at a smart machine or an IoT machine, it is adding an AI or an ML layer in between, so that it gets intelligence into it, where it can take decisions for which you need not write algorithms every time. SCADA system, you have built a SCADA system for, say, energy monitoring. That will do only energy monitoring. It will not do anything else with the data that is getting accumulated on top of it. But if you take an IoT system based on the data that is getting extracted by the machines, you can do multiple use cases without interfering with the SCADA system, without adding new logics into that particular system. So that is the major difference between SCADA systems and IoT systems. And fog architecture is exactly what I'm explaining right now. So it is like a SCADA system without intelligence. So fog architecture is nothing but it extracts data from multiple sensors which are present within LAN. So within local area network, it extracts data from multiple sensors. It does data cleansing, it does data engineering on top of the data which is extracted from these multiple devices, and then sends only the necessary data into the cloud system, thereby optimizing the need for um, even better optimization between control logic and the intelligence part of it. So uh, we initially discussed that why do we need edge architecture when there is cloud architecture? Now the question will come, why do we need cloud architecture when edge architecture is there? Edge architecture does not have any latency problem. It directly takes data from the sensor, it analyzes the sensor, the data from the sensor, and it just spits out. Why do we need another cloud architecture or fog architecture? What is the exact need for this particular thing? So if you see, edge architecture is suitable for intelligence at the sensor level. But if you want to do a historical data analysis, or if you want to run computationally heavy AI or ML models, it is not suitable with edge architecture. For that, you need cloud computing resources, you need GPUs to run multiple iterations, you need uh, uh, heavy computing power to run ANOVA models, ANOVA experiments, DOE, multiple DOE. So this is the reason why there is a need for edge architecture, there is a need for fog architecture, there is a need for cloud architecture. It is on the designers of the smart machines to take a call that which will suit the use case that they have finalized on. So as I said, we have to have a business use case. We should know what data points that we have to capture, what will be the KPI that will be strictly monitored. Based on this, we have to arrive at what is the architecture that has to be selected for the above to meet the above requirement. Then we select the type of sensors, actuators, what communication protocols go into the smart machines. We select these on the basis of the above selection. And then we also we see what are the data acquisition devices for the above selected communication protocols and the types of sensors and actuators. And on top of this, we should never forget cyber security. Keeping all these data and layers and uses in mind, we should never forget cyber security. Before, cybersecurity was not a problem because SCADA systems were completely running on LAN systems. And LAN is not exposed to external internet for any, like, so that there is any vulnerability from any attack from any external resources. But the minute we open those gateways, the IoT gateways, for interaction with cloud, there is a serious security vulnerability that we are bringing into picture. It is giving advantages, but we should also deal with these cases so that we will not be vulnerable. Um, we'll discuss the exact use case of where industrial IoT actually caused a lot of damage to a huge nuclear plant in the upcoming slides. Once this entire architecture is in place, we have to implement a pilot. We have to evaluate the results of the pilot and do a PDCA cycle, and then we have to scale that particular thing. This is how we establish an entire smart machine ecosystem within a factory layout. So, as I said, what is the edge or a fog architecture? Why are they needed? As I said, they are needed because of bandwidth, latency, and connectivity issues. You all know how patchy the connection to multiple data centers has been after the advent of the Iran-Iraq war. Just because some sea cable got severed somewhere, we cannot risk losing production of an entire shop floor sitting somewhere in Tamil Nadu. So this is the reason why only cloud architecture is also a bad thing. Only edge architecture is also a bad thing. So there has to be compromises, and there has to be deeper understanding of what is the exact requirement for us to arrive at the final architecture of what is needed. And we have to have a clear understanding of at what point do we need real-time deterministic control. So what do I mean by real-time deterministic control? If there are systems which run with if-else logic, they will always give the same result. So most of you have seen with AI and ML, you ask the same prompt twice, the likelihood of getting the same result again is very low. So the answers with AI and ML are not deterministic in nature, but that is not the case with if-else logics. If there are if-else logics, you ask a question, and if it is under the purview of that logic, it will always give you the same answer. So where do you need real-time deterministic control, and where do you need complex data processing? So complex data processing falls under the umbrella of AI and ML. It is capable of doing complex data processing, but we are not sure we will get the same response with the same query given to it. So there is hallucination, all these pitfalls are there. So given these challenges, how do academia as well as industry come together and build systems which are resilient and which take the benefits of the new infrastructure and the technology available, but also mitigate the risks posed by the disadvantages that are coming into the picture because of the new technologies and new vulnerabilities that it is getting access to. So what does edge and fog analytics do? So once it collects data from multiple sensors, there is a downsampling that happens. So we need not send the entire data packet back into the cloud. What is a erroneous data, or what is a sample data set? Only that has to be sent. So this downsampling has to happen. And we have to store the data in time series databases after doing fast Fourier transforms. So these computations also happen at the edge or a fog level itself. These computations, if we do not clean the data and we don't send the cleaned data, it will occupy the entire network as well as the bandwidth for the entire data transfer, and it will slow down the entire manufacturing processes. And once we have the Fourier transformed data, which is moving from time series to frequency series, we identify, we filter, and we do anomaly detection, and we send only that particular data into the cloud architecture. So this is what I meant by saying that there is a edge and a fog architecture. So there is a need to balance speed and intelligence. So Deterministic control gives you speed, but it will not give you intelligence. Complex data processing gives you intelligence, but it is not deterministic in nature. So you have to strike a balance between these two by choosing the right architecture for the use case that you have developed, and by building correct models in the cloud to shield your data from irregularities. This also means you have to bring in compute at device level. So because you are not doing compute at cloud level, you are supposed to do the compute or partial compute at the device level. So that is where you have to invest, or you have to research on how do you do model quantization. So most of you are now using chat GPTs and the anthropic models. I'm not sure if you are reaching the limits where it is starting to throw you a error saying you have reached your credit limits yet, but most of the organizations across the world have started seeing this, where they have started reaching their context window limits. They have started reaching their particular credit limits. So if this is the case and we are deploying the entire shop floor whole machines onto AI and ML competency, we should be well aware of our credit utilization, where we have to think of how do you quantize the data that is going in, what parameters should you send, how do you do pruning, how do you do distillation for the knowledge, and how do you deploy GPUs on premises to give you reliable data for the use cases that we are discussing. So edge analytics and fog analytics are key drivers of IoT. There is no mistaking it. But if we have to adopt edge analytics and fog analytics, there is a trade-off where we have to install AI devices locally. And when we do that, we have to be very careful on how much data are we spending, how many credits are we spending. So we have to do an entire research on how do you quantize the amount of data, or how do you quantize the context window that you are sending into the AI models. So coming to the so now that we have established that you need edge devices and fog devices on top of your sensor setup for you to successfully establish a cloud computing IoT setup. But how do you make devices talk to each other? Because servo motor will be of, say, Mitsubishi make. Sensor will be of Omron make. PLC will be Schneider make. So everything has its own protocol. Everything receives data in a different way. So if you see, old age industry protocols were Modbus, Profinet, Ethernet, DNP3. These were the industry protocols that were being used. All these protocols always worked in question answer method. Like you ask something, they give you the answer back to you. If you keep doing this for thousands of sensors in shop floor in real time, that will block your network completely. So yes, old age industry protocols are reliable and they give good time control and they give you real time control, but they will not have any intelligence on top of it. They are very rigid and they don't talk to each other properly. That is why new industry protocols like MQTT, COAP, which is the HTML version of IoT, OPC UA, they have come into picture. Now, they are reliable, they give you real-time control, but they give you with intelligence. Sorry, there is a typo here. DNP3 will not be a new industry protocol. It is only MQTT, COAP, and OPC UA. But it is not a pitfall, but it is something to remember while designing your system, which is you have to do rigorous modeling before finalizing any industry protocol, as explained before. So your industry protocol should be vary of what is the network bandwidth limit, what is the amount of data data packets which has to be sent, what is the latency with which it has to go, what are the devices that are being used for an entire successful IoT implementation. So keeping all these things in mind, you have to arrive at your own protocol and you have to arrive at your own topology. So one other request from academia will be, whenever we are hiring students, they know basic networking like TCP/IP. When we ask them about OPC UA, many students are not aware of that. So the focus has to be more on understanding the data rather than just sending data. Any questions until now?
Sir, no questions in chat box, sir. We can proceed.
Okay. So what is designing a digital thread actually, like what does it employ? There is a CAD system, there is an ERP system, there is an MES and digital twin system. So even for the example that I gave initially, even with the professors who are present here, you all know that all the CAD softwares that are in place right now, they are only tuned for 3D visualization of a machine. If you have to do a virtual twin or a digital twin, you have to embed sensors and you have to embed the actuator data, IO data into that CAD data. Only then will you be able to proceed further. So even in implementation of a virtual commissioning project, we were not able to successfully build a digital thread between CAD and a digital twin. So what happened was, we built an entire machine in one CAD software, and we had to extract the entire CAD software, CAD data into step file and move it to the digital twin software. And then we had to rebuild the entire machine along with constraints with the sensor data in the digital twin platform. So it is not seamless, because if I make any change in the actual CAD data, that will not go and sit in the digital twin data. Someone has to go and manually sync it. So we were creating a siloed approaches between CAD, digital twin, even though we are successfully implementing IoT projects in multiple cases. Same way, there is CAD, then there is ERP software. How do the CAD and ERP software talk to each other? There are then comes the PLM system. So PLM system extracts data from CAD and then it talks to ERP. But PLM software does not take care about the procurement data. It only syncs the material data, the individual part data and bill of material data into the ERP system from CAD system. So there are clear differences between CAD, ERP, and digital twin systems by design itself, because of the product limitations that are present. Implementing a successful digital thread has to be kept in mind when we have to do a as designed. That is, we have to do a CAD as well as a simulation. We have to do as planned, which is ERP logistics, where the data will flow directly from CAD or or from PLM. Either ways is okay, but there has to be a single digital thread which is connecting the entire thing. As built system, which is an MES system, and as maintained. So once we have built a digital thread between these three, only then there will be a successful implementation of IoT telemetry back to the CAD. Or else what will happen is, there is a CAD of a machine, and then that CAD of a machine has to be exported into the digital twin platform, and again some uh, huge amount of man hours have to be spent on top of that particular CAD model. Only after that will we be able to create a digital twin out of it, or else we will not be able to make a digital twin. So it will be like, for the sake of creating digital twin, instead of optimizing the engineering design workflows, we are adding more complications on top of it. So this is becoming another major headache, which academia, software OEMs, industry all have to tackle together, which is becoming a big bottleneck at the moment. And then it is the cyber security aspect, which I talked in depth before. So when we are explaining about concepts of cyber security in IIoT, we have to talk about Purdue model architecture, where it splits the devices within an IoT ecosystem into 5 zones, and it will shield the external interference of uh, uh, hackers or any uh, uncivil elements. It creates layers where it will not allow the corruption from one level to another level. So the first level is internet level, which is exposed, and this is completely shielded with firewall to the fourth level, which is the enterprise dashboards that are in place. That will again have another layer onto ops layer, that will have another layer onto supervisory layer. So the final devices will never get impacted if the outer layers are exposed for any reason. Have you heard of the name Stuxnet anytime? Hello?
Yes, sir.
Have you heard about the name Stuxnet anytime?
No, sir.
So this was a breach. Israeli hackers hacked into Iranian uh, nuclear power facility, and they disabled entire centrifuges using this virus. So this was the first known instance where a connected system actually became a impediment as opposed to an advantage over a connected system. So we all know what are the advantages that are coming. They also believed all these advantages, but they did not focus on the cyber security aspect, and they built the entire system. But it ended up damaging the entire centrifugal system for the nuclear fuel enrichment, because this virus was injected into their connected systems. So whenever cyber security in IIoT is discussed, it should have the literature on how to build zero trust networks at device level, not at a app level, but even at a device level. How do we build a zero trust network? How do we ensure that the hardware that is being used is of it is not a duplicate, or it is like, how are we ensuring that each and every hardware which is in place is actual OEM made hardware. And how do we enable TSN firewalls, which is a time sensitive networking firewall. So most of you have college firewalls which block multiple things. But the problem with these firewalls is they often slow down the performance of ideal websites, of ideal use cases also. So we have to do research on how do we build, not research, but they're already in place. You just have to think on how do we build TSN firewalls which will not impact the performance of intended use cases. So keeping these things in mind, cybersecurity also has to play a very critical role in the IIoT implementation, and this cannot be a afterthought. Mostly what is happening is, because these things are not being kept in mind, what is happening is, even though greenfield machines are being installed, they are becoming a brownfield installations because all these aspects were not thought out while designing the entire IoT system. So uh, as we discussed before, just for the sake of it, IoT, people are creating some dashboards, but later on when their IoT systems are being evaluated for IT regulatory controls, they are coming to know about all these things, and later on they are having to add multiple devices on top of it, which is turning a greenfield installation also into a brownfield installation. So once now we have established that, okay, edge and fog devices are in place, how do you build a app layer inside the cloud? So there has to be detailed information given to the implementation teams on how to build a data ingestion architecture. I am not advocating AWS or Azure here. I am just giving few examples of how these data injection architectures are built, like few examples which are very well known across the spectrum. So there is Kafka, there is ThingWorks, there is AWS IoT, there is Azure IoT. And then there has to be a storage strategy for the data, that huge data that is being pumped in by thousands of sensors every second. So you have to split the data into a speed layer and a batch layer. Not every data has to be stored, not every data has to be analyzed in real time. So you have to build a speed layer which will be analyzed by platforms like AWS Timestream, and there will be another batch layer which will be helping to do historical data analysis, which you can use the systems like S3 to store the data. And then there is a scaling and AI layer. So once you have stored the data inside S3, you have stored inside the data in your EC2 instance. How do you build AI models on top of it? You use already available softwares like Azure Foundry, AWS SageMaker, and you build successful applications on top of it. And then you have your own dashboards, which are part of your company dashboard or your company data lake program. So data lakes are also another big topic in its own, but the idea is the data injection architecture has to feed the data into the data lake, and then you have to split the type of data into storage strategy, and then you have to build scaling and AI layers on top of it, using the services which are already available in the cloud platform that you have chosen for yourself, and then you go and build the EC2 instance dashboards. One other thing to keep in mind when building is, how do we adopt standardized global interoperability standards and consortiums while building IoT systems. Maybe most of you are aware on ISA 995 standards, which are very well known for SCADA systems. But you have to now start utilizing RAMI 4.0 standards, which is Reference Architectural Model Industry. So this is for Industry 4.0. This is a very clear benchmark, or this is very clear guideline on how to build a 3D coordinate mapping layer which has multiple layers. So if you know AutoCAD system has multiple layers on top of it. So RAMI 4.0 also provides multiple layers. First layer will be the 3D data. Second layer will be the sensor data. Third layer will be the device layer. So things like this is very clearly mentioned in the RAMI 4.0 architecture. So this has to be taught, this has to be part of your curriculum, this has to be part of your the projects that you are executing, so that we will have a global standard across which is being followed by multiple teams across the world. And we have to include ISO and IEC 22989 for all disciplines, irrespective of what department they are in. This has to be taught in all mechanical, civil, chemical engineering. Every discipline needs to know about these particular ISO norms, which talks about the key glossary terms of AI. Like what does AI actually mean? This is very clearly standardized and built into these particular standards. We have to build competencies as an organization, as an academia. We have to build competencies in IEC 62443 standard, which is industrial cybersecurity, which deals with industrial cybersecurity. Right now, we are in dire need of professionals who know how to build cybersecurity systems for IoT layers, which is fast, efficient, and scalable in nature. Same way, we have to enable teams on working with ISO 23247, which gives guidelines for building digital twins in a standardized manner. So we cannot go about reinventing the wheel every time we do an IoT implementation. There are standard procedures that are being followed across the world, which can be adopted very quickly and simply. So these things have to come into, so these things should become like ISO 9001. So like ISO 9001 is a bare minimum in our current industries. The same thing has, so in the similar way, all these 4 standards also should become like a very well known term for us to be successful in implementing IoT platforms across multiple projects. Same way, IoT is also enabling multiple teams in meeting sustainable development goals. So there are total 17 sustainable development goals which multiple countries and organizations have set themselves to accomplish these SDG goals. So IoT is the right fit for multiple organizations to meet these SDG goals, which is better data gives rise to better decisions, efficient resource usage, be it electricity, be it water, be it robo utilization, be it human capital utilization. All these things can be tracked effectively with using IoT, which helps multiple teams optimize their workforce in such a way that which will help them make use of the optimal resource usage. Smart cities, as most of you know, smart cities, the bedrock of smart cities is IoT systems in place. where in fact civil engineering is taking huge leaps in terms of building digital twins and smart machines when compared to mechanical curriculum. Water management, as I said, is also part of the efficient resource usage, environmental monitoring, and healthcare improvement. So healthcare improvement is a whole big part of digital twin and IoT systems, which I unfortunately do not have much exposure towards, but I want to expose myself in knowing multiple things, because that is another frontier which is being explored extensively, where IoT systems are being built dozens by the day. So keeping all these things in the mind, what my request is for the academia is to build an academic curriculum which sits in the sweet spot of mechanical, computer science, and electrical, which has a course curriculum which deals with these particular activities, which also deals with the cyber security aspects also. So we need um multiple projects in place in all the universities, where you're building miniature CPS test beds using affordable hardware like Raspberry Pi, Node-RED. If you want, you can build simple systems with 8081 with small microcontrollers also. But you can, if you are successful in building miniature CPS test beds, that will help build a generation of the industry 4.0 5.0 ready workforce, which will usher in new technology innovations across multiple categories. You can also think of aligning senior design capstone projects in their fourth year to match with local manufacturing brownfield challenges, where they want to migrate into IoT platform, they want to build an effective IoT system. So this can be included as part of their capstone projects, which will help them build an effective system. So with these inputs, I would like to pause here, where I have come to an end of my presentation, where I'll open out the session for Q&A, so that we can have the discussion for the remainder of the time. So the floor is open for questions. If any professors have any questions, I'm happy to answer them. Yes, IoT is meant for decision making. So you are not controlling systems where like SCADA, but you are enabling a layer on top of SCADA which helps make decisions in real time by utilizing the compute of AI and ML. For example, if you are doing a tool where use case for any CNC machine, so toolware is not something which can be deterministic in nature. So you cannot say that if the vibration in tool is above this, it is an error. It is a progressive thing which happens. So how will you know at which point will the uh, like should the maintenance take action against that particular instance, so that it will not go to a catastrophic failure or it will stop the entire production. So this decision making is what is enabled by AI on top of the data which is extracted from multiple sensors. Hope I have answered your question.
Dear participants, if you have any queries, you can post your questions in chat box. Else you can unmute yourself and ask questions. I think there is no questions.
Okay. I
Right,
think
sir.
it is such an honor that everyone understood what I am trying to say. This is
Yes,
really great to hear.
yes, sir.
Okay.
Yes,
That's it from my side then. Thanks for the opportunity.
yes, sir. Yes, sir. Sir, on behalf of Knowledge Institute of Technology, Department of Mechanical Engineering, and FDP organizing team, we thank you for your presence and your valuable spend your valuable time and given us insightful talk to us. Hope this session is fruitful to all the participants and beneficial to all the participants, sir. Thank you for joining with us, sir, on behalf of Department of Mechanical Engineering. Thank you for joining with us, sir. Thank you.
Thank you.
Thank you, sir. Dear participants, the next session will be starts by 2:30 p.m. So all are requested to join 15 minutes before for this session. Thank you. Thank you all. We will break for lunch. Thank you.
Okay. Thank you. Bye.
Thank you, sir.
Yeah, hello sir, I'm back. So I sent the request for sharing again.
Hello.
Are you able to see my screen now?
No, ma'am, it's not visible. Please switch on the video, ma'am. And then you.
Yeah. So sharing is not turned on.
Just a minute.
Yeah.
And I take a couple of minutes, ma'am, to make a co-host so that you can share your screen.
Okay. Okay, fine. No problem.
Ma'am, now you try, ma'am. Try to share your screen.
Yes.
Yeah, let me try. Can you see it?
Yes, ma'am. Now it's visible.
Okay, great. Sorry about that. Actually,
No
I have
issues, ma'am.
changed
No issues.
my room and it has some different settings.
Fine. Okay.
Okay. Shall we
Good
start?
afternoon. Yes, ma'am. Okay, let me take a couple of minutes to formally welcome the participants and you, the resource person, and then I hand over to you.
Sure.
Okay. Ladies and gentlemen, good afternoon to every one of you. Thank you for joining the 6-day online faculty development program since this is the fourth day and the post-lunch session. Okay, as announced earlier, Ms. Shweta, Savant from John Deere will be addressing this session and the topic predictive maintenance using machine learning. On behalf of Department of Mechanical Engineering, Knowledge Institute of Technology, I wholeheartedly welcome our resource person of this post-lunch session, Ms. Shweta Savant from data scientist and business analyst from John Deere India Private Limited, Pune, Maharashtra. So, okay, let me formally introduce our resource person of today's session. She holds her academic background from Symbiosis International University and has established herself in the fields of data science, business analytics, artificial intelligence, and machine learning. She is actively involved in leveraging advanced analytics and AI-driven solutions to address real-world industrial challenges. Her professional interests include artificial intelligence, generative AI, machine learning, and data-driven decision-making for engineering and business applications. So with this short introduction, let me once again welcome the resource person of today's session and also welcome all the participants who joined this online FTP across the state. Thank you very much for joining with us. Let you have a fruitful day and fruitful session. And over to you, ma'am.
Yeah, all right. Thank you so much for the warm welcome, sir. So good afternoon, everyone. So basically, I am working with the John Deere as a data scientist for a global machine health team. So today I'm going to talk about the predictive maintenance using machine learning. So you might be aware of what is maintenance. So maintenance is nothing but, taking care of your machine or equipment, to run that machine without failure or, it will not break down. and it will work smoothly. So that is nothing but the maintenance. So we do the maintenance of various equipments like in the manufacturing or in the agriculture industry, as well as we do the maintenance of our home appliance. Okay, so why this maintenance is important? So if you see, the maintenance is directly proportional to your operational cost. Okay, if your maintenance cost increases, your operational cost also increases. Okay, so with that, so sorry. So let's talk about what are the different maintenance strategies the industry is being, following up. So if you see, there are three types of the maintenance strategy. One is reactive, second one is preventive, and third one is predictive. Okay, so we have started with the industry started with the reactive maintenance strategy from 1990s. So what is the meaning of reactive? It is fixing the equipment when the failure happens. Okay, but here again, the drawback of this is there is unplanned downtime, because once the failure happens, then there will be a downtime. And for the big industry like the agriculture, manufacturing, and oil gas, this downtime is very costly. Second problem with this reactive is, unplanned downtime and wastage of labor cost, or emergency repairs. So many times you have to have the emergency calls to the technicians, and they will come and then they will repair your machine, but the cost of the emergency repair is very high. Okay, so to avoid that, in 2000, industry started with this maintenance strategy, that is a preventive. So what is a preventive maintenance strategy? It is scheduling the maintenance at fixed intervals, regardless of whatever is the machine condition. Okay, so one sec. Give me a second. Just check. Yeah. So again, the issue with the predictive maintenance is like we often replace the parts too early. Sometimes, it is not required to replace the parts. So there is unnecessary replacement of the parts. And we replace the parts maybe too early or too late. Okay. So these are the traditional approaches which we were following. And then we moved to maintenance in 2020. Okay, so here what we are doing is we are using AI and ML to forecast the failures before they happen. Okay, so in this, what we do, we use the real-time sensor data along with the historical maintenance records like your warranty data, or if you have any, technician job card, we can use that data as well to predict the failure in advance for any particular machine or the parts of that machine. Okay, so these traditional approaches, lacks the intelligence to predict the optimal maintenance timing. So that's the reason we industry has started following the predictive maintenance strategy. Okay, so to understand or to predict the exact optimal time, or when maintenance will be done, when actually it is not, it is needed, not too early and not too late. Okay, so that is the reason this predictive maintenance is very important. Another thing is, I'll say, yeah. So as per the study from Deloitte research, it is observed that the industry, this predictive maintenance has helped to reduce the downtime by 35 to 45%. At the same time, it has also helped to reduce the maintenance cost. Okay, and how, that I'll explain. So basically, machine learning algorithm, what it does, it analyzes your historical warranty data or whatever data you have related to that machine, maybe from dealer or technician. They call to the helpline and they tell that this is a problem or this is the problem I'm facing with the machine. So that kind of the records of the jobs, that is the historical records that we use for the machine learning algorithms. Along with that, we use the real-time sensor data as well, like your temperature, vibrations, and pressure. And with the help of these algorithms, try to identify the patterns, the failure patterns continuously. And then system predicts the optimal maintenance timing by identifying the early warning signs of the degradation. And maintenance performed precisely when needed. So it is not too early or too late, okay, like in preventive and predictive one, okay. So this is the benefits of the predictive maintenance. So another thing is, as there is no, why there is a reduction in the maintenance cost, because it has a fewer emergency repairs, okay? Because if you have the, reactive maintenance, okay? So the customer will call that machine is failed, so you will have the high downtime, as well as will have to find the labor or the technician immediately to resolve that issue. Okay, and maybe not in India, but outside of the India, like in US and Canada, the labor cost is very high. Okay, so in that sense, if we can predict the failure in advance, it helps to reduce the maintenance cost to to the high percentage. So that is the reason now the industries have started following these strategies. Let's any question till this? Okay, so let's move to the next part. Okay, so what is machine learning? So maybe many of you must be knowing about the machine learning, but I'll just go through it briefly. So machine learning is a branch of the computer science that builds the algorithm to find out the correlation and trends in the data. It enables the system to learn from the data without explicit rule-based programming. Okay. So in predictive maintenance, what we do, we convert our raw data into actionable insight, and it helps to predict the failures in advance. Okay. And so this is very important point, because something is happening. Okay. Okay, so it is not about only building the machine learning model, but it is about how you can convert your raw data into actionable insights. So much of data goes inside the model, and then it analyzes the pattern, and then it provides you the prediction. Okay, but before providing the prediction, a lot of data processing happens at the back end, or we have to write what we want to do. Like for example, the feature engineering, it is another I'll say the part of the machine learning. So now let's look at the key application of the machine learning in predictive maintenance. Okay, so with the help of the machine learning, you can do the anomaly detection. So what is the meaning of anomaly detection? It takes the abnormal patterns related to your telematics data, like vibration, temperature, engine load, engine speed, indicating the early faults. Okay, so in this anomaly detection, when it is used, when you have the less failure data, okay, or you do not have any failure data. So in that case, this anomaly detection is being used across the industry, wherein what we do is we pass the machine raw data or the sensor data, which we capture at every second. What is the temperature, what is the vibration, or what is the DPF, how frequently it is happen. So all this raw data we pass to the model, and that model identifies the normal behavior of the machine. Okay, and once it identifies that pattern of the normal machine, then whenever it gets something deviation from that normal pattern, then it identifies as an anomaly. Okay, and in that case, then it triggers that anomaly, that there is some anomalies found in that particular raw data, and then you can capture those anomalies, and then we can trigger the machine that something is wrong with that machine. Second part is the failure prediction. So what it does, it estimates the remaining useful life, that is RUL, which is commonly called as RUL, using historical and the real-time data for just-in-time maintenance. Okay. So in this case, it gives you, for example, for bearing, it gives you how many days it can be, after how many days it may fail. Okay, so that it gives you the idea of when to change that bearing. Okay, and in advance you can be, get ready with the, what are the parts is needed for that maintenance. Along with that, you can schedule the technician, schedule the maintenance time as per the availability of the customer or the dealer on the field. So this is the failure prediction. Mostly we use the XGBoost and the regression algorithms for this, so that I'll explain you in upcoming slide. Then the third one is the pattern recognition. So what it does, it identifies the complex relationship between different telematics parameters like the load, temperature, and vibration to detect the hidden failure signals. So this pattern recognition, it is little complex. There are thousands of parameters. For example, if I take the example of the John Deere machine or the tractor, there are so many sensors on the machine, and this sensors captures the captures the telematics measurements at every second. So there is a huge data, and there are thousands of parameters for one single machine. Okay, so if you want to identify, recognize the pattern, many times you have to combine the different telematics parameters. It's not that simple, like for example, if this particular temperature goes beyond 85 degrees, trigger the alert or trigger the machine. But sometimes it is very complex. You have to combine so many parameters together and then identify the pattern. And then after recognizing that pattern, then what model does is it whenever we support any or whenever we give any real-time data to that model, it finds out whether it is, if there is that pattern is there in that data. And if it finds that pattern, then it shows that there is a possibility that this machine is going to fail in near future, maybe in coming days or near, in coming weeks. So that is nothing but the pattern recognition. And the fourth, but which is very important, is optimized maintenance. So it aligns the predictions with the operations to minimize the downtime, cost, and resource usage. So what exactly it does, now we have the prediction, we have the probability, failure probability of the machine, that, the model says that there is a probability of 85% that this machine is going to fail. But after the prediction, what it does, it combines that prediction with your parts inventory, so whether that part is available or not, then the technician availability and maintenance period. So many times what happens, some operation is going on the field by the farmer, and we cannot directly go and tell them that, we want to do this, apply this solution to avoid the further, failure. So we have to take the time for their machine. So this optimized maintenance, so in this machine learning algorithm helps to combine all these parameters together and prepare one maintenance plan for that particular machine, so that we can avoid, last moment failure, which can cause the high downtime. So this is about the key application of the machine learning in predictive maintenance. So any questions on this? I hope I am audible. There's no disturbance. Can someone
Yes, ma'am.
confirm? Yeah.
Yes, ma'am.
Okay.
Carry
Great.
on.
Yeah. Now let's move to the next part. Deploying the machine learning for predictive maintenance. Okay. So just building the machine learning algorithm is not the goal, right, for the predictive maintenance. How you deploy that machine learning algorithm and how you continuously learn from that prediction, that is also important. So I have tried to put some, points here which we need to follow if we are deploying any machine learning model for the predictive maintenance. So first step, which is very important, is finding out the eligible machine. So in our case, or in the manufacturing or the agriculture industry, so what we do is we first find out what are the frequent issues happening in the field, okay? And then second part is we find out the machines or the parts which is causing the high warranty cost to the company. And depending on that, we decide which machine population we want to target for the preventive or the predictive maintenance. Okay, so that is the first step whenever we deploy any machine learning model. Okay, the second step is the data preparation, which is very important. See, building the model will not take the time, but the data preparation, data cleaning will take more time, and that is the very important step because until whatever you give to the model, if you're giving the good data, you will get the good result. If you're giving the bad quality data, it will give you the bad prediction. So that is the reason this data preparation part takes, a lot of time. Maybe I'll say the 60% of the time we invest in data preparation than, building the machine learning model. So what we do here is we just clean the data. So like in our case, we have 1 hertz data. So at 1 hertz or at every second, we, capture the measurements. Okay. And it is a huge data. So sometimes it has the noise data or the missing values into that. So if we give the missing data to the model, obviously it will not give the correct prediction. Okay, so for that reason, it is very important to clean the data, process the sensor data, remove the noise, handle the missing data, and create the useful features. Okay, so as I mentioned earlier, the feature engineering is one of the part of the machine learning. Okay, so there are maybe 20 to 30 parameters or the telematics parameters which impacts the failure or which contributes to the failure of the particular part or the machine. But many times what happens that all these parameters are maybe, so what we do is we combine 2-3 features together. For example, there are 3 features like temperature and pressure, but if they are highly correlated, okay, then we select only one of the those parameters. We do not pass all the parameters to the algorithm. The one reason is the data is huge. Okay, so if you pass a lot of data, thousands of parameters to the algorithm or the model, definitely it is going to fail. So this part is very important to decide which features or the parameters we need to pass to the algorithm so that it will give the correct prediction. That is called the feature engineering. So in this, what we do is we do have the correlation matrix wherein it gives you the correlation between, multiple parameters, whatever the parameters we have selected for that model or, the raw data we have. And then the parameters which are having high correlation, maybe more than 90%, we just select one of, if there are 2 parameters which has the 90% correlation, we'll select only one parameter out of it. So that is correlation matrix. And the feature engineering, another part is the feature importance. So we do have some algorithms which provides the feature importance. So if you give the raw data to that model, it gives you which feature is contributing more to the failure of that part or the machine. So accordingly, you can select the data or select the feature. Okay, if there are, let's say, 20 features we are or the 20 parameters we are passing to the model, and then it processes the data and it gives you the feature importance, and according to that it observes that there are only 10 parameters which are contributing to the failure of that particular part of the machine. So in that case, we will not select the entire 20 parameters, we will select only 10 parameters. So these parameters are nothing but the features for our model. So this step is very, very important for the machine learning model. Third point is model training and the validation. Okay. So in this, we just train the model using the historical data and the live data. We use various techniques like regression, anomaly detection, neural networks, depending on the use case, depending on the availability of the data, and what kind of the problem we are solving. So on the basis of that, we decide what type of the techniques or the algorithm we are going to use to predict the failure. And then after doing this, once we have the prediction, then we pass or we do the internal validation. Okay, so for example, in one of the project I worked on is IVT transmission pump failure. So I developed one model and I send the prediction to the SMEs. These are the domain expert or the field, representative. Then they what do is they contact with the dealers or the customer to actually check for 2 or 3 machines whether that pump is actually failed or not. Okay, and once it is confirmed, once we do that dealer validation, then we deploy it to the production. Okay, this is to avoid the false positive. Okay, so we do not want to send the alert to the machines which are not actually failed or which are not going to fail, because it may cost high charges, the labor charges as well, if it is the machine is not going to fail, because the technician will have to open the entire machine to check whether there is fault or not. Okay, so in this case or in the such scenario, the confidence level is very important, and for that reason we do some internal validation as well before deploying into the production. Then deployment and monitoring. So run the models in real time to detect the anomalies and predict the remaining useful life. So what are the prediction of the model we have developed? We pass the real time data to that model and continuously we monitor it. Okay, whether we have any anomalies for any machines or the parts, or if it is giving any prediction for the remaining useful life for any of the parts, or if any part is going to fail in coming days or the weeks. And then the next part is continuous improvement. So we use the maintenance feedback to retrain the model to improve the accuracy of the model and reduce the false positive. So what we do into this is whatever the feedback we receive, as I mentioned, we receive the feedback from the dealers whether that whatever the prediction we have done is correct or not. Okay, then we pass that feedback to the model again. We fine tune the model so that we'll get the more accuracy. And this is a continuous process. This is not the one time activity. This is to make our model more error free, or to get the accurate predictions, and to reduce the false positive. So the false positive are nothing but the machines which are not fail, but our model is predicting it as it is going to fail. Okay, this is very dangerous. We should not have a lot of false positive, otherwise it may impact the customer experience as well as the cost of handling or performing any solution on the machine to avoid that failure. And the last part is the workflow integration. This is just to connect the prediction with the maintenance system. So as I mentioned before, we use this prediction, we combine this prediction with our system, like the technician availability, the parts availability, and the maintenance period or the maintenance availability of the machine or the customer. And then accordingly, we prepare the maintenance plan for that particular machine. And then, we decide what parts will be needed, to avoid that failure. So whenever there is a prediction, what we do, we collect, or the technician do is, it collects those parts in advance and then go to the farm to repair a particular machine, so that it saves your time. Okay, to come back, to collect that part, whatever part is needed to avoid the prediction. Just give me a minute. Okay, maybe we can continue. Sorry, I was losing the room, but now it's okay. Yeah. So I think someone has put, okay. Okay, yeah. So this is about deploying the machine learning algorithm for the predictive maintenance. Any question till this? Are you able to understand what I'm saying, or is it too technical, or it is too slow or too fast? Can anyone give me the feedback?
We have a question in chat box, ma'am.
Okay. Yeah, I have open name of the algorithm that choose for the feature engineering. Okay, so there is no any specific algorithm for the feature engineering. Feature engineering is nothing but the processing of your features. The features are nothing but your telematic parameters. Okay, so there is no any specific algorithm for that. It depends. So as I mentioned, there is a correlation matrix which we can use. Another one is the feature importance, and there are some statistical methods as well, like Z value, P value, that we can use for the feature engineering to decide which features we should be, use to predict the failure. The next question is how to plan for material requirements in predictive maintenance. Okay, so basically, I'm a machine health team. I am not much, connected to material requirements, but yes, we do have the domain experts. So in our machine health team there are two teams. One is the people who develops actual machine learning algorithm or the model, and another team is the domain expert. Okay, so they know for particular problem. Okay, what they do is once we develop the prediction, they develop the solution as well along with that prediction, that if this is the problem, okay, what solution dealer has to apply or the custom has to apply to resolve that failure. And in that solution, they talk about what materials or the parts needed to work on that solution. So that will be done by the domain expert. So we combine all these data from the domain expert, that is called as interactive solution, and then we combine that with our prediction, and we send all this data as a trigger to the machine. Okay, so that information comes from the domain expert. The next question is, could you provide the GitHub link or the code that is used in any of the project? Oh, okay. Maybe I can provide you the general code, but not related to my project due to, it is confidential. We have the IP team here, so they have, strictly told us not to share any project or, the code. But yeah, definitely, maybe after this meeting, I can share you some, generic code, which, you can use for the predictive maintenance, or I can refer some project as well. I hope that will work for you. All right. Let's move to the next part. Okay. So what are the different machine learning techniques? I think you might have heard about this, but still, I'll just go briefly about these techniques. So one is supervised learning and second one is unsupervised learning. So what is the difference between this? The supervised algorithm is trained to classify the data or make the predictions based on the known input or the output data. Okay, so basically, for some of the issues, we already have the failed machine data. There are some machines which are already failed because of that issue. So in that case, we already have which machine has failed and which machines are non-failed. So that is nothing but the labels, non-failed, failed machine. So in this case, it is called a supervisor algorithm, wherein we have the information about the failure machine. That is called the supervised algorithm or the supervised learning. Second is unsupervised learning. So what is the meaning of this? This discovers the hidden patterns by analyzing the unlabeled and unstructured data. Okay, so what is the meaning of unlabeled data? Here we do not have any failure machine data. This failure is happening for the first time, or we want to detect the failures which are unknown, okay, which has not happened till date, which are unknown and which is causing subsequent failures or the damage to the parts or the machines. Okay, so in this case, in such cases, we use the unsupervised learning. Under supervised learning, again, there are two types. One is the classification and second one is the regression. So the classification helps to divide the input data into different classes using both input and output. So what classification does is whatever the data, raw data I'm passing to the algorithm, it gives me the classification whether that machine is going to fail or non-fail. Okay. Another example is if I want to predict the failure modes of that particular machine, that is a classification algorithm. So what kind of the failure it will be, whether it is particular, which part A failure or part B failure or part C failure. So like that, it gives you the classification. Second one is regression. It explains or the predicts the specific numerical value by analyzing the past data for similar properties. So for example, DPF pressure. Okay. If in case of DPF issue, if you want to do the regeneration, in that case, it gives you after how many machine hours you have to do the regeneration. So in that case, we use this regression type of the algorithm. And in simple, in layman language, so if you want to predict the, house prices, okay, based on the, inflation rate and based on the square feet, all this you can do with the regression that is called a linear regression. Under unsupervised, we have the clustering. So what it does, it explores and analyzes the input data to find patterns or the groups in it and classifies those data points into specific cluster. Okay, so as I mentioned before, it gives you the different type of the failure modes. Okay, so for one machine, if there is one failure, but it might have the different failure modes. Okay, so it helps to bucket that machines into different failure modes, because depending on the failure modes or the buckets, your solution which you are going to apply to resolve that failure will change. So in that case, we use the clustering algorithm. So this is just in brief, I tried to explain you. These are the different machine learning techniques and use cases I just copied from the internet, and these are the different examples or the use cases on what type of the algorithms you can use for what type of the cases. Okay, so for example, classification. Yeah, you can use for the data classification, facial expression classification, text classification, speech recognition. Also, you can use SVM algorithm, cancer detection and diagnosis. Then we have the Navy base. Again, it is you can use for the classification, for the spam filtering. For example, in the email, whenever any new email come, it in Google in Gmail you might have observed that some emails are automatically going under the spam folder. Okay, so in that scenario, in that situation, we use this classification algorithm wherein it reads that email and based on the past data, it identifies whether it is a spam email or working email. Then document classification, supply chain, stock management. These are all the classification type use cases. Linear regression, sales forecasting. So mainly when you want to forecast anything, the linear regression is, helping, will help you. So it is whenever you want to predict any continuous value from the input data, then we use the linear regression. Like investment evaluation, stock price forecasting, real estate price analysis and prediction. So what will be the cost of this particular, location or the area in future after the 5 years or 10 years. So in that case, you can use this regression algorithm. Then we have the neural networks combination. We can use the combination of the regression and clustering as well. Okay, so fraud detection, then virtual assistant services, financial risk assessment, machine translation. So these are the good examples of the neural networks and the regression and clustering. Then customer segmentation. So like in Amazon, they use this customer segmentation algorithm to maybe even in the hotel industry or the travel industry, tourism. they use this to find out the premium customer, or the depending on the customer requirements, or depending on the what type of the data is being searched by that customer, it put that customer into particular bucket. Okay, and depending on that segment, it creates some travel plans or the discount plans for that particular segment. Okay, so for that case also they use the clustering. So these are some examples outside of the manufacturing or the agriculture industry. So let's move to the next part. So if you see here, I just tried to put what type of the algorithms are being adopted by the industry for the predictive maintenance. The first one is the random forest. Okay, so it is more than 70% adoption rate. Then we have the XGBoost. It gives very good accuracy. Then we have the LSTM algorithm. So this is the deep learning algorithm which helps for processing the complex time series data, time series sensor pattern. Okay, so mainly when you have the streaming data, okay, in that case we use the LSTM or the deep learning data. Then random forest and XGBoost are the example of the supervised learning, wherein you know or you have the information about the failure machine, and then it helps you to classify health status of the particular equipment. Okay. And unsupervised, again, the anomaly detection is a kind of the unsupervised learning. So isolation forest is one of the example wherein we pass the raw data, and depending on, then it calculates the average standard deviation of that raw data, and depending on the deviation from the normal pattern, it gives you that there is an anomaly detected against that particular machine data. So that is the anomaly detection. So these are the different ML techniques is being used across the domain. Now let's talk about the predictive maintenance workflow. Okay. Again, so if you see on the right hand side, I have mentioned the real time. Okay. Okay. So there are two ways of storing the data or the capturing data. One is real time and another one is cloud based. So the real time data is nothing but the streaming data, which gives which helps you to immediately find out the anomalies and the response. Okay, so mainly the Netflix and other what do you call aviation industry, in that we use this real-time data, wherein the time factor is very important. If there is any problem is going to happen, it should immediately trigger based on the real-time data. And the second one is cloud-based. So in John Deere, we use generally the cloud-based data. So it is not immediately, we want to know the failure. Okay. So we have the 1 Hertz data, that is, we track the measurements for every second, and we pass that data to the cloud. We store that data to the cloud. Okay. So it is not exactly at the same time we extract the data and detect the anomaly. So in the cloud-based platform, it helps to process the vast sensor data volumes from the distributed asset. Okay, so in this, the infrastructure cost plays very important role, because if you want to have the real-time data, streaming data, your infrastructure cost is high. And again, it depends on the use case. If your use case is, if you do not want the streaming data or immediate data, then we go for the cloud-based data. Then let me talk about the workflow. So first part is, or the first step which I mentioned earlier as well, is the sensor collection. So like in John Deere tractors, we have multiple sensors, and we track the parameters from those sensors, the telematics parameters like temperature, pressure, vibration, engine load, engine speed. Okay, so we continuously monitor, tracks that data and store in the cloud system to generate the health metrics. Then data integration, what we do is we combine this sensor data or the telematics parameters with the historical data. So as I mentioned, we have the warranty data. Okay, for the particular machine, whether we have received any warranty before and how many parts before hours we have received that warranty. So based on that, we sorry, we integrate the data. Just give me 1 second. I'll have some water. Okay, so this is about the data integration. We combine the data, the sensor data with the historical records. The third part is ML analysis. So what we do is we develop the algorithm or the model to analyze the pattern and calculate the failure probability. So what is the probability of this particular machine is going to fail in future? Okay, and depending on that failure range, maybe if a particular machine there is 80% or 90% of the failure probability, we just target those machines and trigger the solution or the alert to that particular machine. Then prediction output, system generates the risk scores and the failure time estimates, and then the maintenance actions. So as I mentioned before, we combine all this prediction with our maintenance system, like the technician availability, labor availability. Then we have maintenance periods, and then parts availability, and then we prepare the maintenance plan for that particular machine or for that failure, and then then the technician or the dealer follow that maintenance plan, and then it applies, or whatever the solution is provided against that failure, it just go to that particular customer, it applies that solution. If there is a part replacement, it will take that parts along with him, and he will go to the field, he will replace that part. So all that part comes under the maintenance action. So this is about the workflow. I think there is a question. Let me check. When we have the large amount of the data, time series data, which algorithm is better, LSTM or random forest? For the large amount of the data, I'll say the LSTM is the better algorithm, because it works very good with the time series data. Okay, and random forest is good, is also good model, but it will not be good for the time series data. It is good for the accuracy and large amount of the data, but the time series data you will need to have the LSTM algorithm. I hope you got the answer, Virendra. Okay, thank you. Let's move to the next part. Okay, so let's go through one of the example. This is just the generic example I have taken. So let's assume that there is a hydraulic pump. So the hydraulic pump is very important component of the heavy equipments, for example, the tractor or excavator, which fails unexpectedly. Okay, let's assume that it is failed, okay, unexpectedly, which is causing the production downtime, expensive repairs, and secondary component damage. Okay, so if you see here, the important part is it don't fail suddenly. Okay, it shows some early warning signals like vibration, temperature, pressure changes. Similar to human being, if there is heart attack, it doesn't comes immediately, or it can be predictable, or it shows some warning sign that your cholesterol, if you do your health checkup, okay, it shows your cholesterol level has increased or some other parameters. So all these are the warning signs before the failure happens. Okay. So what what we do in this case is, first we try to collect the data. Okay. Uh, Before collecting the data, like while collecting the data, it is very important to understand whether we have that data or not. Many times what happens that we do not have each and every data to create the model. For example, in one of my projects, we are not having the vibration sensor to the machine. So it is very difficult without vibration signals or the vibration data to predict the bearing failures. Okay. So in such cases, first of all, try to find out what data you have. Okay, whether you have the temperature data, vibration data, current data, pressure data, and maintenance log, depending on your use case or the problem. Okay. Once you know that you have the sufficient data, then just collect that data, okay, real-time data, and then combine that data with your historical patterns. So historical pattern is nothing but whether that machine has failed before as well, or has it thrown any DTC. So in John Deere, we have the DTC, that is diagnostic trouble codes. These are nothing but the error codes. Okay, if any of the parameters goes beyond the threshold, it displays some DTC codes on the displays of that particular machine or the tractor. Okay, so in this while building the model, we also consider the DTC code as well. Are there any DTC triggered before the failure happened? Is there any combination of the DTC happening before the failure happens? So all this analysis we do here after collecting the data. And that is nothing but the data processing that comes in the data processing part. So here we clean the data because we do not want to pass the bad data to the model. Otherwise, it will give you the bad prediction. Okay, we remove the missing values, or we sometimes if there are any null values for any parameters, we replace with the mean value or the average value, depending on what problem you are solving. Or sometimes if our entire record is showing null value, we just remove those values from our entire data set. Okay. And what we do in this data processing part is we remove the noise and outliers. Okay. Sometimes what happens for example, in the temperature is very high. It is it is called as outlier, which is, I'll say, whatever the maximum allowed value for the temperature, it is going beyond that. So we do not consider those outliers because there is some problem with system or maybe tracking that data. So we just remove those outliers from the input data. Otherwise, it will give the wrong prediction. Then we handle the missing value, and then we create the features. So as I mentioned before, sometimes we, for example, for isolation, forest, anomaly detection, we give the raw data. And for classification or other data, we first calculate the average value of particular, for example, the temperature. So within last 30 minutes, what is the average value of that temperature or the pressure? Okay, because why we do is to understand the pattern, okay, through the average or the standard deviation. The standard deviation helps you to find out if there is any spike. Okay, even the average also helps you. And because the data is very huge, it is very difficult to pass the raw data directly to the model, because model will not perform efficiently if you pass the raw data. So many times we have to do the feature engineering. We have to calculate the average, standard deviation based on whatever the time period you select, maybe for the 15 minutes, last 15 minutes, last 30 minutes buckets. Okay, so and then we pass this data to the model for the further prediction. So after passing this data, what it does, it learns from the data to identify the patterns and anomalies linked to the failure. Okay, so as I mentioned before, there are different type of the models. The anomaly detection detects the unusual behavior. So if what it does, it detects the normal behavior of the machine from the raw data, and whenever it finds something is out of that normal behavior, the deviation is very huge, in that case it triggers that there is an anomaly or there is some outlier. Then regression model, in this we predict the remaining useful life. So how this is helpful is, suppose there are different bearings in one machine. Okay, so generally in preventive maintenance, what we do is after 6 months we replace all the bearings. Okay, but in this predictive maintenance, for each and every bearing we calculate the remaining useful life, so that if one bearing is in good condition, we will not replace it. We will replace only the bearing which is in the bad condition, okay, which is going to fail in coming days. Okay, so that you can save the cost of whatever the cost is you'll require for that part. Okay, and then the neural network, it is to detect the complex pattern. Now the next step is pattern detection, the real insights. Okay, so what it does, it is a combination of the vibration, temperature increases over 200 hours, the pump failure likely in next 50 hours. Okay, so this is one of the example of the insights. Okay, how it provides the insight. Okay, or how it detects the pattern and what is the meaning of that. Okay, for example, on the right hand side I have put one table. If there is increase in the vibration and rise in the temperature, it means that there is a bearing failure. If there is a pressure drop or increased current, there is a seal leakage. If there is a sudden vibration spike, there is an imbalance or the misalignment of the part. Okay, so depending on the pattern, the combination of the different parameters, or the pattern, it gives you the insight what problem is going to happen with that machine, whether it is a bearing failure or fuel leakage or any other problem. Okay, so this is the real insight which helps SME or the field people to identify the exact failure and provide the exact solution to avoid that failure in future. Then this is the example of the prediction output. Okay, so the early warning alert is potential pump degradation detected. Okay, so it is not showing that the pump is failed or is going to fail within one day. Okay, so here early warning means it is giving you enough time to schedule the maintenance. Okay, so it is degrading. Okay, it is not yet failed or it will not fail immediately. So this is very important to get enough time for the maintenance and replace the part on the customer's machine. Then it also gives you the RUL, that is remaining useful life estimate. So example is failure expected in 40 hours. Okay, so you have the 40 hours of time. Within 40 hours, this we can the model is predicted that this particular bearing is going to fail. So just plan for that, get those bearing, give it to the technician. He will go to the field and then he will replace that bearing in advance, depending on the customer availability or the machine availability. Then the root cause hint, the possible bearing fatigue. Okay, so this also gives you the root cause. What is the root cause of this particular alert or the trigger? Then the last part, or the second last part, is the maintenance actions. As I mentioned before, is predictive maintenance helps just-in-time maintenance instead of the reactive repair. Okay, so here what we do is whenever we have any trigger, okay, failure trigger for the machine, the solution which is already developed for that particular failure, we send that trigger to the machine or the dealer system along with the solution. Okay, and the solution is interactive. So what we do is we build the flowchart type of the solution, wherein we ask the technician whether the temperature is between this or between this value, okay, 0 to 80. If yes, then follow the solution A. If no, follow the solution B. So there are different type of the conditions we have in the solution, and depending on the the value selected by the technician, it gives the appropriate solution to resolve that failure. Okay, and this solution is prepared on the basis of lot of your historical data, like in the warranty data. For example, in the past we have received any warranty, and then we analyze what corrective action have been taken to resolve that particular issue. And then based on that, whenever SME or the domain expert develop the solution, it considered that solution, and then it adds that solution as a part of interactive solution whenever we send the trigger to the machine. Okay, so many factors are connected to this. It's not only the real-time data, but the past data as well we utilize to provide the appropriate solution. So ML systems, the last part is continuous learning. So after repair, what we do, actual failure data is fed back to the model, and model improves the accuracy over the time. So it's not like, as I mentioned before, it is not a one-time activity. So whatever the actual failure happen, okay, or the prediction happen, we give that data back to the model. And again, if there might be some false positive as well, when we deploy this model to the production, so we give this type of the data to the model as well, and then again it fine tunes the model. It checks, oh, this is this factor also the model needs to consider, and then again it rebuilds the model and it gives the more accurate prediction. So this continuous learning part is also important whenever you are deploying any machine learning model for the predictive maintenance. Yeah, this is the end of the presentation. So maybe any question we can talk about that. Are you guys able to understand what I tried to put? The basic things. Not I avoid to put the technical things here, because not everyone is technically expert like machine learning, algorithm, coding, and all part. Okay, so I try to keep this presentation as a generic, so that at least you will able to understand the concept. See, building or the coding can be done, from the people who are technically expert, or now you have the Copilot or the Chat GPT. It gives you the ready-made code. Okay, but understanding the concept, understanding what actions you need to take whenever you want to deploy any model to the production for the maintenance, that understanding the background is very important. So any question, feedback, or anything you would like to know more about? Okay, one question from Virendra. Suppose we have to do predictive maintenance of DC motor. What is the basic step we have to follow? Okay. So again, as I mentioned, depending on the, again, I am not a mechanical engineer. I am from computer background. So if it is a hydraulic or the mechanical part, okay. So in that case, the vibration data, the vibration sensor data is very important. Okay, if it is electrical part, then you have the current, load, engine speed. Okay, so according to what part failure you are trying to identify, your parameters changes. Okay, and this actually I'm from system health team, so the domain expert are the people who provides these measurements. Like for this particular part failure, I want to track, or I want to concentrate on these parameters, the telematics parameters. Just analyze these parameters, develop the ML model, detect the pattern, and then give me the prediction. Okay, so this is the common process which we follow for any type of the prediction or the developing any model. Okay, so as I mentioned, it is very important first to check whether you have the data or not. Okay, related to that failure. If you have the data, whether you have the sufficient data or not. Many times what happens, we do not have the sufficient data, and if you have the less data, you will not able to develop a good model for the accurate prediction. Okay, so that is also important part. Please provide a mail ID for. Yeah, sure. I'll provide you my mail ID. Not a problem. Is there any question I have missed? How much cost saving annually by following the predictive maintenance in John Deere? Oh, again, I can say in percentage, not in numbers, because it is at the global level. So almost I'll say 20 to 25% we have achieved the cost saving using the predictive maintenance. And still, as I mentioned, it is a continuous learning. Now with the help of the AI, we are targeting to achieve more cost saving with the predictive maintenance. Yeah. So there are a lot of, projects are already going on to improve this cost saving. In factory, so what are the number or the percentage I have told? This is overall, combining all the factories at the global level. It is not only a single factory. Okay, so I do not have that data readily available for a particular factory. What is the cost saving? One more thing which I missed to mention is whenever we develop any machine learning model, we come across one challenge is imbalanced data. So what is the imbalanced data is we have only 10% or the 5% of the failure data and only 95% of the non-fail data. Okay, or maybe 10% of the failure machines data and 90% of the non-fail machine data. So in such scenario, if you pass all this data as it is to the model, obviously it will, give the prediction more towards the non-failed machine, because it will, analyze more data related to non-failed machine as compared to failed data. Okay, so in that scenario, we have couple of, workarounds or the algorithms called the SMOT. Okay, so which helps to balance the data. There are different ways. One way is create some synthetic data for the failed machine, so that you will have the 50% of the failed machine data and 50% of the non-failed machine data. And another way is reduce the non-failed machine data. So if you have the 10% failure machine, just consider the 10% of the non-failed machine, so that you will have the balanced data to pass it to the model, and then it will give you a more accurate prediction. Any other question? So I'll just type my email ID here for your reference. So anytime if you have any question, you can send me email. I'll also share this PPT with you. So maybe after this meeting, I'll ask sir how to share this, because the size of the PPT is large. So I'm not sure whether I'll be able to share it through this chat window. But maybe I'll email it to the sir, and then you can distribute this PPT whoever wants it. Okay, that's it from my side. I'm just stop the sharing.
Okay, ma'am. Okay.
Yeah.
Ma'am, we will get the PPT from you, ma'am, and we will share to the participant.
Yeah.
Okay.
That would be good.
Participant, if you have any queries, can ask, or else we can end up today's section. Okay, ma'am. I think it was a wonderful session. Thanks for accepting our invitation. On behalf of Knowledge of Technology, I thank you, ma'am, for this wonderful session. And we have very much informative about the predictive maintenance. Hope we will have a future conversation for our any other research purpose also, ma'am. Thank you for your support, ma'am.
Sure. Anytime you can contact me. You can send email to me whenever you need any help from my side.
Sure, ma'am. Thank you, ma'am.
Thank you so much. Thank you, everyone. Bye. Have a nice day.